I'm happy to jump right in.
All right.
See if I can share my screen again. We did test this, so hopefully it will work. Is that still working?
Looks good.
Okay, great. Yeah, thanks for the opportunity to talk at ASCAC. This is the first ASCAC meeting I've actually attended, so it's been quite interesting for me, especially to hear yesterday about all the very well thought out planning being done for the future. And it was nice to see all those highlights from all the different applications that ASCAC supports. For my talk, I'm going to talk about our work getting an Earth system model running on exascale, or getting ready to run on exascale computers. It's a big effort. I have a lot of collaborators. I didn't list them all here, but I at least like to acknowledge the projects that support this work. The E3SM non-hydrostatic atmosphere NGD, that's led by the Next Generation Development sub-project led by Peter Caldwell. The Oscar-funded Exascale Computing Project, the E3SM Performance Group that's led by Phil Jones and Sarat Sripathi, and the CMDV Software Modernization Project that was led by Andy Salinger. See if I can. So a few years ago, DOE reorganized their Earth system model development efforts and all focused on a single model now, E3SM. That's the Energy Exascale Earth System Model, led out of BER. It's a rather large project, for at least for what I'm used to, about 70 FTEs spread over 8 DOE laboratories and several universities. We have a science missions really focused on energy and water issues, looking out the next 40 years. And our main computational mission is to ensure E3SM is ready to run on DOE's upcoming exascale computers. The project is led by Dave Bader at Lawrence Livermore, and the chief scientist is Ruby Long at PNNL, and I currently serve as the chief computational scientist of the E3SM project. There'll be a little bit of confusion because there's the E3SM model and the E3SM project. Today, I'm also going to talk about results from sorry, I want to move these Zoom videos out of the way. The Oscar-led ECP project. This is also an exascale project focused on a more, I'd say, higher risk configuration of the E3SM, referred to as E3SM MMF. It's based on a multi-scale approach, often informally referred to as superparameterization, and that is particularly well suited for GPU acceleration. And then since this is ASCAC, I wanted to mention, but I won't be talking about this in my talk today, but there's a lot of work being done under the SIDAC project. And that's also relatively large, about 10 FTEs spread over multiple projects. And that's done a lot of this SIDAC over the years has made a lot of key contributions to the E3SM model. And it has more of a focus on algorithms than on porting to new architectures. And in my opinion, that's good because algorithms remain one of the new algorithms and research in algorithms, one of the most impactful way to improve the E3SM model. Oops. This slide is the brief summary of the overarching science drivers of the model. We have 3 centered around the Earth's water cycle, biogeochemistry, and cryosphere systems. Not my specialty, so I'm not going to go into these, but I wanted to have this slide in here just for background and future reference. So we're focused on exascale, and now for the rest of my talk, I'm going to our exascale strategy is basically how do we run on GPUs. So it's now our GPU strategy. And this is because all the upcoming DOE Office of Science machines will be GPU-based. NERSC, Perlmutter, Frontier, replacing Summit, and Aurora. So really, I'm going to use GPUs as a substitute for exascale. And I want to start just summarizing the key points. These I certainly apply to E3SM. I think they broadly apply to probably all Earth system models, but they are application specific and don't apply to all applications across DOE. But the first point, which I think is relatively well known, and we see this in our data, is that the CPU performance on traditional CPUs, and this is all normalized on a kind of per watt basis, has nearly stagnated. We have data, I'll show later, going back to 2012, and we see basically a 2x speed up over the last 6 years. So not completely dead, but relatively modest improvements. GPUs, on the other hand, can provide today a 3x speed up per watt over today's best CPUs. For those of us used to working in the era of Moore's law, a 3x speed up is a little bit underwhelming. But if you compare that to what we see on CPUs, it's quite good. And if you need hardware acceleration of your code, it's really the only game in town. If you want that 3x speed up waiting for CPU trends, assuming these trends even keep up, it would take 8 or 9 years before you got that. But it does come with some caveats, this GPU speed up. It's really only in what we call the high workload regime, and I'll talk about that next. And then to get that 3x speed up really requires a lot of work. And for us, it either basically rewriting the code from scratch or major refactors. Related to this caveat is that traditional climate simulations are usually throughput limited. We want the model to run as fast as possible because we run long simulations, and so we strong scale out to where there's little amount of grid points per node, the low workload regime. So traditional climate models struggle to get this benefit. And in E3SM, we really want to focus on new types of simulation campaigns where GPUs will provide a real benefit over CPUs. We want to run things on GPUs that you couldn't do on equivalent CPU systems. So we don't want to spend a lot of time and money porting our code to GPUs and then run problems where the original code, if we had done nothing, would run just as well on a CPU. So some examples of what I mean by the high workload regime for GPUs. I have 4 here. The first is the X is what we don't think will run well on GPUs. And this is where traditional Earth system models are run, where you make century-long or 300-year, 500-year control simulations, really long simulations. And you have to run them, you can't spend years making one simulation, so you have to hit these throughput rates of about 5 simulated years per day to make those practical. So you're trying to make the model run fast, and so you strong scale out, use lots of cores, and you get into the low workload regime. So this type of simulation really is better suited for CPU clusters, and a $5 million commodity CPU cluster will run your traditional code very efficiently in this regime. And this is responsible, I think, for a lot of the difficulty we've had, or the time it's taken to really make effective use of machines like Summit. But we've identified several new simulation regimes or science campaigns where GPUs will provide a real benefit, and I've listed them here. The first I want to mention is ultra high resolution, or commonly referred to as a cloud resolving model. This is where you run at resolutions necessary to resolve the cloud formation processes responsible for storms. It has a lot of computational advantages, or improving the models. This is represented by E3SM SCREAM project. And they're going to run great on GPUs, but to put it in perspective with the traditional campaign, a typical NSIDE award, when you run at this resolution, since the model is so expensive, will get you about 10 to 30 simulated years. So it's a different type of simulation, but a lot of exciting science can be done here. The second regime is to increase the local complexity of the model. So do a lot more work for each grid point, but don't add more grid points. And this is the focus of our ECP project, the MMF, or superparameterization. And the superparameterization approach can achieve many aspects. It's not a complete replacement, but it can achieve many aspects of cloud resolving models, while also still running at the throughput rates for these longer, century-long simulations. And in some sense, it's been more, I guess, more directly suited for GPUs, and we've been running these on Summit since the beginning of Summit through the OLCF Early Access Program. The other one, the cloud resolving model, most of that work is done, but it's not completely done, and we expect it to be running scientific simulations in 2021 or 2022. And then the last regime, which I won't talk about here, is instead of going for this 3x speed up, use the GPUs to be more efficient. So you can convert that to a 3x savings in power, meaning for the same power bill, you can run 3 times more simulations by running large ensembles. And this is one thing we've learned is that for this to really get that improvement, we need the entire model, all components, running end-to-end on the GPU, which is targeted for our V4 release. This is just some comments on our programming model and how we try and achieve both performance and portability. We've basically narrowed it down to 2 approaches, and we have large investments in both of these approaches across different components of the Earth system model. Fortran and OpenMP and C++, basically rewrite, most of the code is traditionally written in Fortran, but rewriting key components in C++ using Cocos for the GPU acceleration. Both strategies, I think, ultimately can achieve the same or similar levels of performance, but they both require basically complete code refactors or complete rewrites to really get that true GPU performance benefit over CPUs. But it's an opportunity, because if you are going to completely rewrite your code, we're taking the opportunity to improve a lot of other aspects, especially in testing and software engineering, and we add verification, from the very beginning throughout the whole development process. It's taken us each major component in the Earth system model, and there's 4 or 5: atmosphere, ocean, sea ice, land ice. Land takes several years to rewrite or refactor, and it's not just simple porting that you could contract out. It really, at least the first time, requires a lot of computational research along the way. So many of our key findings come from this paper, this GMD paper from last year. And I have a couple highlights on this slide. This is work with the atmosphere dynamical core with and without tracers, so it represents about half of a full atmosphere. We have great data for these components going back to 2012, so a variety of CPUs, several generations of GPUs, as well as the KNL architecture. And what I'm plotting in these plots is the performance of the model, basically some kind of normalized performance, roughly equivalent per watt, and higher is better on these plots. They're all only single node performance, so they don't include all the overheads of a real model like the MPI and the communication between components. So in some sense, they represent the best case. Since they don't include these overheads, we know the full model can only at best achieve the results we see here. There's 2 plots because there's 2 main components we've looked at the atmosphere dynamical core, which is really struggles to eke out even a small benefit with GPUs, and the atmosphere dynamical core when we add 40 tracers. And these two extremes, in the case with tracers, that's on the right, you see there's one curve, which is the red GPU. It's higher than all the others, showing the benefit of GPUs. These two, we think these two extremes represent, as all the other components of the model will be, roughly speaking, somewhere in between these two extremes. So the one on the right is gives us an upper bound on our performance, and we do a lot of our performance estimates and design our campaigns and our strategy based on these results. And we'll soon add some newer CPUs, EPICs, and the new Fugaku ARM processor, as well as the new GPUs. We'll add them to this when they come out. So if you take that work, it's, like I said, about half of an atmospheric model. It's missing some of the parameterizations, but it has all the MPI, and it's can run these realistic configurations using this NGGPS benchmark. This is a standardized benchmark from the National Weather Service. It was used in their next generation global prediction system work, choosing some of their software components. And it's been quite useful because it allows us to compare machines and models from different modeling centers, all in a standardized way, and really get a measure of trends and hardware. I've summarized some highlights in this table. The first line in the table, let's see if I can point, is from the original National Weather Service work, and the one of their fastest models, and the model they ultimately went with, NOAA or GFDL FV3 model, running on Edison, the large machine at NERSC at the time, which is a 2.6 petaflop in the LINPACK benchmark. And in this work, they obtained a throughput rate of 0.16 simulated years per day. So far from the 5 simulated years per day we would like for some climate simulations. But this was several years ago. And then since then, there's work on the home dynamical core, and that's the dynamical core used both in E3SM and the CESM. There's a big Chinese effort to port this dynamical core to the Sunway Taohu Light machine, which was the #1 machine at that time, 125 petaflops. And they got this dynamical core running in this benchmark at 0.34 simulated years per day. And then our work in E3SM, we've both upgraded the model to non-hydrostatic, which is really necessary for these resolutions. That's the NH, and then rewrote it in C++. So that's home XXNH. Running on the full Summit system, a 200 petaflop system at 0.97 simulated years per day. So nice steady progress in the community across machines and models. Interesting point though is not surprising if you follow the kind of LINPACK benchmarks versus the HPGC benchmarks, is more typical for applications. We see, for example, going from Edison to the Sunway, huge increase in LINPACK performance, 2.6 to 125, but only a 2x speed up in our application, the core of the climate model. Summit's actually doing a little better in that respect. It's less than twice as fast as the Sunway supercomputer, yet it's 3 times faster in this realistic application. So this data, we give a lot more details in this recent supercomputing paper, including the strong scaling. It's what I show in this plot. On Summit out to 27,000 GPUs, and also our performance portability work is documented in this paper, where we compare the new C++ code both on GPUs and on CPUs and KNL, and show that it's also still competitive and even slightly faster than Fortran code. And then we also have run at even higher resolutions, this blue curve on the plot is a 1 kilometer model. So that's actually 1 trillion grid points running well on the Summit system. Okay, so that was the first application which we're close to running on GPUs and will run well. And the next few slides are our second application, the ECP project, this MMF or super parameterization approach, which has been running now for several years and makes very good use of GPU acceleration. In this multi-scale approach, it's similar goals as a global cloud resolving model. It replaces the structural uncertainty in these parameterizations that are necessary if you're going to approximate cloud processes with a cloud resolving super parameterization. So you take a global model at a traditional resolution, and in each grid cell, and this is depicted in this picture here, at each grid cell, the approximations done in there are replaced by a super parameterization. And from the name, you can imagine it's much more expensive than the traditional parameterizations. And then you have all this work to offload to the GPU and benefit from GPU acceleration. So GPUs won't make this model run faster than the original model, but they'll allow us to dramatically increase its complexity and have it run at the same speed as the original model. So it's really an ideal approach for GPU acceleration. And this multi-scale approach will make it possible to achieve some aspects, I say, or hopefully many aspects of a global cloud resolving model while being much more affordable and much faster. Here's one slide looking at one such issue. This is the Madden-Julian oscillation, or a fingerprint of the Madden-Julian oscillation, one of the dominant modes of variability in the tropics, and one of the things that traditional models struggle with and cloud resolving models can do a good job at. So on the left is observations. It's kind of a complicated plot showing outgoing long wave radiation as a function of longitude and time. But the important feature is the red and alternating red and blue bands have this slope to them, and that's representing the eastward propagation of these features. Notoriously hard to capture in a traditional model at traditional resolutions. That's the plot in the center. And then the super parameterization approach doing a very good job, not identical to the observations, but dramatic improvement in this eastward propagation of these bands. And the super parameterization approach does run well on GPUs. Here's some data showing that. In this MMF or super parameterization model, the performance is dominated by this 2D super parameterization referred to as CRM because it is itself a 2D cloud resolving model. Porting just the CRM to GPUs is sufficient to make use of GPUs effectively. So since it's such a dominant cost of the model, we have this one key kernel, we get that running on GPUs, and we have a nice way to run on Summit, which is why, as I said before, it's been running for several years now on Summit. And the performance, so we look at the performance of the CRM, the dominant cost of the model. And again, we see the similar trends. This plot shows performance is now a different axis. It's runtime, so higher is slower, smaller is better. And this shows performance as a function of workload. So it's the number of CRMs we are running per GPU. And so that really shows that you need to get to the high workload regime where you have, say, 5 to 20,000 grid points each with a CRM per GPU. But in that regime, you get these dramatic speed ups. And in this code, the red bar is the Fortran code, original Fortran code running on the CPU. And then the green, blue, and orange are different approaches to GPU performance. The green is the rewrite into C++, and the red and orange are Fortran with restructuring and then adding. We started with OpenACC and now we're transitioning to OpenMP compiler directives. And you can see from these results that the Fortran OpenMP approach is good, large speedups, but not right now not competitive with C++. And this is, we think, due primarily to compiler maturity issues. We expect eventually it would be sufficient, but if you want to run right now or in the near future, your best bet is probably C++. So just some closing thoughts. CPU systems are continuing to get better. As the recent Fugaku, the machine in Japan that's now #1 on the top 500 list. GPU systems are also continuing to get better. We'll soon have the exascale machines, Frontier and Aurora. In E3SM v3, the model to be released in a few years. We'll have two approaches, both centered around cloud resolving simulations that will be made possible by GPU architectures where we can run simulations on the GPUs that I think we couldn't run on the CPUs, or they'll run more faster or more efficiently on the GPUs. And then by the time we get to V4, we're confident our strategy will allow us to run the full model efficiently on both architectures, both CPUs and GPUs. And hopefully this will help us be prepared for any kind of even more exotic post-exascale hardware that shows up. Thank you. I will stop here.
Thanks, Mark. Questions?
Hi, Dan.
Yeah, go ahead.
So a couple of questions, Mark. Great presentation. Good to see that the super parameterization allows you, brings in, I guess it brings in much greater complexity and so allows you to make much better use of the GPU's performance characteristics, right? I mean,
Yep.
is it n squared rather than, you know, n squared flops per word, or how, or what do you know roughly what it is?
So it's, you mean in terms of the increased complexity? It's,
yeah, per word.
I can get you that number, but I don't know that off the top of my head.
Right, because you know the challenge with a lot of this stuff is, I mean, I keep banging on my little drum about this. A lot of it is basically, you know, order one, you know, order one flops per word.
So
and
we're not, sorry, that arithmetic intensity, we're probably not increasing because we're bringing in a CRM that's still a conventional low flops per memory access. What we're doing though is we have so much work that we can use all the threads of the GPU simultaneously with no synchronization. And in a sense, the reason we see this 3x benefit is because we're relying on the bandwidth improvements of the GPU.
Right, and that was my question. So when you go to Fugaku, which has the same bandwidth, roughly speaking, as a Summit node, you might see similar performance. And that's a sort of, and that's the issue with a lot of these codes, because a lot of your code is order one flop, you know, it's one flop per word essentially. Yep. And so that then raises the issue of the second point I was coming to, which is, can you sort of measure, you know, it's good to see the energy efficiency, but have you also thought about the cost and the cost when you include the amount of rewriting time, because you're talking about several years worth of time and however many hundreds of, you know, person years. And so, you know, the trade-off there is kind of interesting in the sense of it'd be good to document this in some way, because it sort of, it ought to, you know, I mean, that's the issue with present applications. I mean, the things that you're doing with cloud resolving is exactly the way that you should go, which is you should use the power of the GPUs to increase the complexity of models and get better science out of it. But for those people who can't rewrite the codes, it's not clear that the GPU option is necessarily a sort of a viable thing to do, because they don't have the resources to do the rewrite. Yeah.
And that's one thing that I often ask, and I don't know that anyone knows for sure, is that the trends, are the CPU trends and the GPU trends going to continue in parallel, or will the GPUs slowly pull away from the CPUs? Well,
it also depends a lot on the design, because it's as you say, for many applications, it's the key thing is the memory bandwidth, and it's a question of how those next generation of machines are actually designed. But great presentation, thank you.
Thank you.
Yeah, Rich has a question.
Yeah, thank you, Mark. Again, great presentation and such important work, and a great exemplar of the importance of high performance computing. And it's in its application today. I had a question, wondering if you could elaborate on the software engineering that you're doing. You mentioned you're taking the opportunity to do verification and validation of the code as you're rewriting it. Correctness is such an interesting and important problem. I'm curious what tools and approaches you're using for that, that correctness and verification and validation in that software engineering.
Yeah, so I'll give the example of the Screen project because they've probably done the most thorough job. But so unit tests, which is when you have all this legacy code, no one wants to go back and put in unit tests, but when you're rewriting from scratch, we write every subroutine with the unit test. And the one thing we're doing right now, because we have this Fortran code, is every C++ routine to start with the unit test just verifies bit for bit with the Fortran. We run in special modes where the code is bit for bit. That's kind of an easy way to get started. And then we add what we refer to as property tests. So simple properties, as many as you can think of, mass conservation, should be maintained by that subroutine and tested individually, rather than the traditional approach, since these codes have a lot of legacy behind them, are kind of full functional tests, not these small component tests. And then we add, for example, in the physics, convergence tests in special regimes, you can do convergence if designed carefully of single components, like convergence in the number of levels, things like that. And then we've also added automated testing. You know, everything is now on GitHub with pull requests and nightly testing, automated testing through.
Marco, is there any role for formal methods? You know, formally specifying the correctness conditions in that process?
You know, our experience is testing is expensive and it takes a lot of time, but the more testing, the better. And we have several people on the project that have really been pushing this hard and have are slowly convincing all the scientists this is a really good idea. So I don't know enough about formal methods to know for sure, but my answer would be the more testing, it can only be better.
Thank you.
Other questions?
Yeah, I have a clarification question. This is related to the comment about the performance gap between Fortran and C++. I saw that the C++ comparison was actually C++ and CUDA. So I'm wondering how much of it is really a comparison between handwritten CUDA code and compiler generated GPU code from OpenMP rather than Fortran versus C++. Perhaps you might get the same. Yeah, so that's
yeah. It's not. Oh, it says CUDA there. It's actually not handwritten CUDA. It's a C++ array class called YACL. You can think of it as very similar to Cocos. YACL is like a version of Cocos that's a little easier to use with code coming from Fortran. So it's not direct handwritten CUDA, which we did early on, but have decided not to pursue. Also, it's not a performance portable.
Right. Yeah, that's partly why I was asking.
Yeah.
So, but
so that's C++ with an array class, all the GPU code generated, you know, behind the scenes with C++ technology, not handwritten CUDA. Yeah.
And I'm not familiar with that library. So that C++ class, was that GPU code handwritten, or was there some compiler tool that was used to generate that code? Not by you, but whoever developed that class.
That's a good question. And it's Matt Norman. I don't know the answer to that. I don't think it's CUDA. I think it's the back engine for YACL, but I don't know that. Sorry.
Okay. There may be some lessons there to learn for folks doing the OpenMP implementation. So that's why I was curious.
Yeah.
Thank you.
All right, Rich has one more question and then we should move on.
Yeah, thanks, Mark. A couple of years ago, Lawrence Berkeley Labs was architecting a special purpose computer called Green Flash or Green Wave. I think it was both names. And it was along the lines, excuse me, of the Anton machine for molecular dynamics, but in this case applied to climate. And I believe the target was the cloud resolving models. Subsequently, I think the Allen Institute has looked at building special purpose hardware. In your opinion, is there a role for specialization of hardware for this important application?
Well, if we could, certainly if we could design our own machine, we had in this in E3SM, we now have a little bit better idea of what that would mean. I wasn't involved in the green flash work, so I don't know, at that time wouldn't have understood how to do that. So I think there is a role for that, although I don't know that it's commercially viable. In some sense, where DOE GPUs have a lot of benefits for some applications, much more dramatic than we see in climate. So there will be those machines. So somehow I feel our role is to make sure we can run cloud resolving effectively as well. But yeah, it's a good question. I don't know. We don't really know the answer. How much better you could do with custom hardware.
The question, commercial viability, if the mission is critical enough, then the commercial viability consideration might be something to set aside.
Yeah, there's a long philosophical R&D question about whether, as we're running out of steam with traditional semiconductor advances, whether the pendulum is going to swing more back to ASICs for code acceleration and that dynamic. But that one is maybe a long conversation for another day, but it's a really good question. All right, so Mike and Rajiv and Jeff are going to take it away to give us an exascale update. And so Mike, the floor is yours.
Thank you. You can hear me?
Yes.
Great. Can you see my screen? It says I'm paused. I'm not sure.
We can see it.
Unpause? You can see. Great. Excellent. Okay. All right. Going to full screen. Can you see the slides? Right view?
No.
We can. You're in presenter view, so we can see this current and the next slide.
All right. Hang on. How about now?
Yes.
Yes.
Whoops, I tapped it twice, sorry. How about that?
That's good.
All right, very good. All right, well, thank you for the invitation to come and speak. We'll have three presenters, myself, Rajiv, and Jeff. We'll try to keep our direct comments, each of us, to about 15 minutes, if possible, to leave some time for questions. So the first thing I want to point out is the leadership. We had a leadership change recently. Overall, we've been very stable in our leadership. Many, these people quite well, I think most of you. But recently, we've had a new member join, Catherine Moore, who's also from Lawrence Livermore, replacing Rob Neely. Rob Neely, strangely, because of Michael McCoy's retirement, that led to Chris Klaus moving in for Michael, and then creating an opportunity for Rob to take Chris's position. So although we're sad to see Rob go, we're very happy to have Catherine join us. She's a rising member of the DOE community, and she's made great contributions already. We want to say many thanks to Rob for his efforts. In fact, he was part of ECP leadership from the very beginning, and it was a little bit of fun to reminisce with him through some of the thoughts of what occurred early on in the project. So welcome to Catherine, and thanks to Rob. Second thing we wanted to mention, a couple of changes in our L4 teams. We've added an L4 level 4 project, sub-project. These are the individual PI projects, one called ExaWorks, which is looking at workflow capabilities with a modern software twist to it. Their intent is not to create another workflow platform, but to look at the components that go into workflow platforms and create componentized versions of capabilities that can then be brought in and help to standardize the software architecture of existing widely used workflow tools. And the people involved in the project have a long time track record of working on a variety of workflow tools. So we're hopeful for some real progress there. The second thing I wanted to mention, simply because PETSI is such an important part of the software ecosystem, that Barry Smith has retired from Argonne. Todd Monson's taken on his PI role. But mostly I want to mention that because, not to raise alarm, but because Barry's actually very strongly involved still in PETSI development, perhaps even more so than in the past as an associate. And so we don't anticipate any risk, with his official departure as a PI, but in fact may see, more contributions from him in the near future. I want to mention a little bit about what we're doing to track progress within software technologies. And as you may recall, ECP has 4 KPPs, key performance parameters. Software technology is focused on the 3rd of those. And what we're trying to do is track capabilities and the integration of those capabilities into our stakeholder environments. So a capability is defined as a significant product functionality that may roughly approximate an FTE over a year's worth of effort. So it's something substantial. And then integration means that it's sustainably integrated into the stakeholder environment. Often that's a library into an application, but it can also be a tool that is used by applications, like a performance monitoring tool to give insight. And so it can be capabilities integrated into the vendor stack. Our MPI capabilities, for example, LLVM efforts, which Jeff is going to talk about. These are things that get integrated into software stacks that exist outside of ECP, but are still important to track. We're fortunate to have a really nice JIRA dashboard for managing KPP3s as a special issue type for us. We have our development teams update their present value, that's their status, their score, and their integrations that they've performed. At least twice a year, we encourage them to do it as they get capabilities integrated into their stakeholder environments. What's noticeable about this graph here is that we can count the number of the tentative present values. And right now we have 21 of the 63 KPPs achieving the passing value that's required using tentative present values. We don't have exascale systems, so we can't measure it on there. That's the final measure of success, but we can at least see our status relative to these tentative present values. So KPP3 measures the key value proposition. What does it mean to be an ST? That you provide capabilities that other people want to use, and you do so in a sustainable way. We've benefited greatly from our review team's inputs, who have provided excellent advice over the years. In particular, Bill Carlson has been, a really good voice for us in helping us refine what we mean by this metric. The use of JIRA and real-time tracking is very important for us. And also I wanted to mention that, this notion of capability integrations is not peculiar to ECP. It's really a widely usable technique or concept that can be applied to projects outside of DOE and future DOE projects. The next thing I want to mention is a little bit about E4S. E4S is mentioned in the ASCAC report that was discussed yesterday. It's a collaborative HPC Linux ecosystem. What it provides is a couple of layers. As we've probably seen, and that DOE's delivered high value software for many years, reusable software. That's not new. What is new is our ability, because of the institutional arrangements that we have, to create cross-institutional efforts, our software development kits and E4S itself. And it's been a very powerful way to create a portfolio of capabilities. These are the components. It's mostly a leave behind slide of what we provide. We can build from source, we can build from containers. E4S is available in cloud platforms. We have GPU builds for AMD and NVIDIA, So we're providing a lot of access points for people who want to use E4S. So I want to mention a couple of new things that are going on that are quite new. And one is our community-driven quality commitments. You've seen perhaps if you've been paying attention to the Math Libraries SDK, the XSDK community policies. These have been very powerful statements of quality commitment on the part of team, commitments to our users, so that we can address some of the issues of people not wanting to depend on a third-party piece of research software because they're not sure that it's going to be high enough quality and that it's going to be sustainable and around for them as they go forward in time. We've taken this approach and we've migrated it out to other SDK teams. And the first phase of that is to actually have a set of candidate policies for what it means to be a part of the E4S stack. And we're preparing a version that will be available by the end of this calendar year. I just grabbed a snapshot of what's currently out there, just so you can kind of see essentially what we're getting after with this effort. I want to mention that the community policies are certainly important as a collection of policies and also as a set of membership criteria for the future. For the Math Libraries, the XSDK, these policies are in effect the entrance criteria for becoming part of the XSDK. We foresee the same thing happening with the community policies for E4S and the other SDKs that we're working on. But as important is our community discussion that's occur. These policies that we've created for E4S and the Math Libraries are hard-fought discussions about what it means to provide quality to your stakeholders. And that conversation it builds community, it builds a deeper awareness of what's essential. So that's also a very important part of what we're doing with quality improvement through these policies. The next thing I want to mention is our documentation portal, which is again new. So what we're trying to provide is satisfying some user challenges, finding specific information for a product, finding new products, trusting the accuracy of this, and presenting it in a hierarchical way. From a developer's perspective, we want this to be this tool that we provide, this portal, to be efficient and effective and to allow them to get noticed by new users and to convey both summary information and details about the product. So the portal strategy has been to have all the content related with any product reside in the product repository. If it's out of date there, then that's something the development team has to fix, but we do not have stale data. We cache it if say a link is down for a day or two, but otherwise we rely upon the information that is in the product repository. And then we ask for minimal information from the development team in how we get access to that. So I want to mention that the doc portal is alive. You can go and try it out right now. If you go to e4s.io and then click on doc portal, you will get to this page here. A few things noticeable about it is it's searchable. You can search for things. It's sortable. You can sort by the name, by the area, by the description, and other attributes as we go forward. Once you click on one, and I just selected audios, you get an expanded window of raked information. This has been just raked from the audio site within the past day. So it's quite accurate. If you then want further information, there's a link to go right to the audios homepage where the details exist. And this is the basic model of what we're providing. So what do we ask from teams who provide content to the doc portal? Just a URL, just a link to their repository. And then we take that and look for metadata information, for example, the contributing, the copyright, the license, the README file. So adding a new product to the doc portal is simply having them provide a URL to us and then making sure that their metadata files are in place and that we have a lot of flexibility about how to prescribe where your metadata are. And then making sure that that information is up to date. All right, I want to mention a little bit about our build pipelines that we've created because they're very powerful and start to show some of the value of our curated software stack and the use of SPAC. So we have a large and growing build cache for E4S. that has now more than 10,000 binaries. And basically what we're using is a very powerful feature of SPAC, where if SPAC sees a signature of a build of a particular package, we can cache that build. And then if SPAC sees that signature again in the future, it doesn't have to do the build again. It can simply go and grab the pre-built binary data from this cache, and it dramatically reduces build times. The WDM app team has started using this, and in fact, they have integrated how to use the E4S build cache into their documentation portal. This is just a snapshot of their documentation. And then most recently, we've had the Pantheon team start to use this approach, and they've seen build time improvement of 10x. And talking with David Rogers, the actual improvement from the previous ways they used to do this, because they didn't have access to curated, versioning and software capabilities that were just turnkey. They've actually seen roughly 100 times improvement in their build times by adopting this workflow and the technologies that we're providing. And you can say that SPAC provides the technology behind this. It's absolutely true. What E4S is bringing to the table is the actual effort of keeping versioning and reducing this so-called dependency hell. And then eventually, as we are already doing, providing the latest capabilities for the exascale and pre-exascale platforms. So this is just a summary of what E4S is and is not. It's not a closed system. It's not monolithic. It's not a commercial product. It's not a simple packaging of the existing software. Instead, it's all of these other things. The last thing I want to mention is we've been reaching out to the broader community and getting a lot of resonance and interest in collaboration. Just yesterday, part of why I'm a little bit tired today is that we just, thanks in large part to Samir Shendi and the two of us working with others to have the second extreme scale or E4S forum. This is a list of the presentations, and I bolded the names from people who are not at, part of DOE. We have the Swiss Supercomputing Center, NASA Langley, University Tech TU München, Ohio State, Dan Stanzioni from TAC, and Sato-san from Riken all gave presentations at our workshop. And then you can see also from the other presentations, the variety of interaction that we're having with E4S. So just to paint a bit of a picture for E4S, emerged as a new top-level component in the DOE HPC community, enabling fundamentally new relationships. We're having conversations with facilities, with collaborators that were never possible before, because what we had were these smaller projects. Now we're a portfolio. We can speak with an aggregate voice, and that's very powerful. We can expand to new domains. ML and AI can be a part of this effort, very natural way, by just creating another technical area. And we can really get better, faster, and cheaper by using the approaches that we're creating. This is just a bit of a summary slide. I won't speak to it so much because I've said most of these things, and I want to keep on time as much as possible. I don't know if you want to ask questions of me now. We're going to transition to Rajiv and Jeff. So if you want to ask a few questions now, but otherwise we can move on to Rajiv.
Questions for Mike before we go on? Okay, Rajiv.
Yeah. I'm Rajiv Thakur. I lead the programming models and runtime area in ECP. And I'm going to talk about progress in projects in our area and performance portability. So the DOE systems that have been deployed so far, as we all know, have had either multi-core CPUs or GPUs from one vendor, NVIDIA, whereas the systems that are announced going forward so far, they all have GPUs and they all have GPUs from multiple vendors. So here you have AMD, Intel, and NVIDIA GPUs to deal with. So what that means is that all software projects have to adjust to this new reality where they must support GPUs and support them well, and they can't just target NVIDIA. They have to have support for multiple vendor GPUs. So next slide. Mike, it's not advancing for me at least.
Okay, sorry.
Yeah.
Is that better?
Yeah, now the next slide, yeah. Yeah. So what does this mean in terms of programming between nodes and programming within a node? So because of these powerful GPUs, the individual compute nodes are getting very powerful. And as a result, you don't need a very large total number of nodes, such as on the Blue Gene-like systems. So in terms of the inter-node programming model or the communication library for inter-node communication, there isn't as much stress on scalability to millions and millions of nodes. Rather, it needs to play well with whatever is the intra-node programming model being used. That is the hybrid programming aspect, be it threads, or now with the GPUs, it's mainly integration with the GPU programming model and taking advantage of the GPU memory and making sure that all the memory movement is efficient, GPU to GPU with minimum host involvement and so forth. So that aspect of the communication library is important. There is always work to be done in taking advantage of the specialized hardware that will be there on these new platforms and the new low-level communication paradigms and the new interconnects, enabling low latency communication and optimizing collectives and the overall resilience and robustness of the product as well. And MPI is expected to continue to serve this role for most applications. PGAS models such as UPC++ are also available, and there are some applications in ECP that use them, such as the ExaBiome code. And they face similar challenges to MPI on exascale systems. That is, they need to work well with the GPU programming model. Next slide. Then the main challenge is achieving performance and portability. No, it went too far. Within a node. So there are multiple options here. There are vendor-supported options from NVIDIA. We have CUDA and OpenACC. From Intel, we have SYCL and DPC++, which are C++ abstractions on top of OpenCL. And from AMD, there is the HIP model, which is similar to CUDA. And then there's OpenMP, which is a portable standard, and it supports accelerators via the target directive, which has been part of OpenMP since the version 4, and there have been improvements in future versions. It is supported by vendors on all platforms, so it's a portable approach. Now, of course, there are improvements needed in the implementation of that. Then there are the COCOS and Raja efforts. These are developed at Sandia and Livermore, which are portable heterogeneous programming via C++ abstractions. And on the back end, they support multiple CPU and GPU types. And many ECP applications are using these approaches for the performance portability. Next slide. Yeah, so the AD, the application development focus area in ECP issued a milestone report in March of this year, which is available online, and the link is at the bottom of the slide. It's an excellent report in that it has a lot of detail about ECP applications, so I recommend that report in general. On the last page of that report, which is like page 193 or something, it's a big report, there's a table that lists the programming models used by ECP applications, and there are multiple codes within each application. So all those have been listed, and it's on this slide and the next slide that I've produced that table just to show. Yeah, you can go back to the previous one. That the codes are using a variety of languages. There is a mix of C++ and Fortran as the main language. Then on the GPU programming model side, again, there's a mix of approaches. Some are using OpenMP, OpenACC, OpenCL. Some are using CUDA. Then there are others that are using libraries, such as provided by the co-design centers in ECP, the AMREX and SEED and so forth. And yeah, next slide. And a similar story on this slide as well. This is not a static, static table in the sense that this is what they're going with going forward. There's a lot of exploration going on with other programming models. There are more applications looking at some more applications looking at DPC++ and experimenting with it for the Intel platform. This is just to show you that there's a variety of intra-node programming models being used. Cocos and Raja are quite widely used. Next slide. This is the portfolio of projects in the ECP programming and runtime, programming models and runtime area. There is an SDK effort led by Samir Shende, and Mike covered some of that effort in his talk. There are two MPI projects, the MPitch and OpenMPI. MPitch is led by Pawan Balaji at Argonne, and OpenMPI by David Bernhold. And they are both focused on enhancing the MPI standard and the respective implementations for exascale. And both of these are quite widely used. OpenMPI is used on Summit and Sierra today, and MPitch is the primary, going to be the primary on the exascale platforms. There's the Legion effort led by Pat McCormick at Los Alamos, and it includes the Stanford group, Alex Aiken. There is Parsec led by Jack Dongara and George Bosilka at UTK. Both of these are task-based efforts. There is a PGAS effort led by Paul Hargrove at Berkeley, UPC++ and GasNet. And Cocos and Raja, which I'm going to talk about next. And there's the Argo low-level resource management for OS and runtime led by Pete Beckman at Argonne, and it includes Maya Gokhale and Tapasya Patki at Lawrence Livermore. There's one more project. There's the OpenMP or the SOLVE project, which was part of this area in the first half of ECP, but in the second half, it has been moved to the development tools area in order to keep all the LLVM related efforts in one area. So that's in Jeff Vetter's area, and he'll cover it in his talk next. Next slide. Yeah, so Cocos and Raja are C++ portability abstractions developed at Sandia and Livermore, respectively. They were primarily funded by NNSA, but ECP ST has provided additional funding to them to develop optimized backends for Aurora and Frontier using OpenMP and SYCL DPC++ as well as HIP. And for outreach to ECP applications and math libraries and other software products. Both these efforts are organized as one project in ECP ST, and as a result, the two teams they are collaborating on common features and C++ related support, common backend support, and on outreach activities. This combined project is led by Christian Trott at Sandia, who leads the Cocos effort, and Rich Hornung from Livermore, who leads Raja, is a co-PI on it. But there are 4 other labs also involved, and there is development work happening at all the 4 other labs as well. So this is really a multiple lab project involving 6 labs. Yeah, next slide. Yeah, so Cocos has roughly 3 components. There's a Cocos core, which is a C++ template-based library for the programming model. There are tools for profiling, debugging, and tuning that connect to this core. And there is a Cocos kernels math libraries effort based on Cocos, the core, which is also part of this of ECP ST. And it has a distributed development team, as I mentioned. They also work closely with the ISO C++ standards organization, and they participate actively in it so that Cocos features can be pushed back into the standard, and the standard provides the functionality that Cocos needs. For example, the C++20 standard was recently voted in maybe two weeks ago or so, and it has one feature that came through this Cocos participation in it, and it's the atomic ref class template, which is for atomic operations. And there are a couple of other features that are being considered for the next version of C++, which is C++23. And Cocos is used on most DOE platforms and even on European platforms such as the PIS-DAINT effort. It's widely used across ECP projects. This is probably the most widely used of the programming models efforts, other than MPI, of course. You know, Exawind, Exalt, WDMA app. There are a bunch of the co-design libraries use it. There are some software products that use it. And of course, the Sandia and LANL ATDM apps also use it. And COCOS does a really exemplary job of outreach and training activities, probably the best of all projects in this area. They have held many boot camps at the various labs. These are 2 or 3 day efforts where they work closely together with the applications on their code. These are moved online now. They used to be in person. They've given tutorials at SC and at PESC and other events, and there's any amount of online material, including YouTube videos and so forth on COCOS. And this has helped in the adoption of COCOS. Next slide. Yeah, so this is an example of a production run on an application, the Sparta code, which is a direct simulation Monte Carlo code from Sandia. So this code was run on all of the Trinity system. And Trinity has 2 partitions. One is a KNL partition and the other is a Haswell partition. And this code was run across both of them, across all roughly 20K nodes, using MPI features to run the multiple executables and COCOS to manage the compute part of it. And few applications are run that way across the whole system, across both partitions. This is one that was run across the whole system. And it was also run on 16K GPUs on Sierra, because with COCOS, you can run it portably on different types of architectures. In terms of the support for exascale hardware, so they have access to the early access hardware at the facilities, and they run and test there. So they have on COCOS 3.2, the current version, they have support for HIP for AMD GPUs, currently missing some hierarchical parallelism and tasking due to compiler bug. So they stress both the C++ side of it as well as the backend side of it, and they help find bugs in these early versions of the software, and they are getting fixed. So even on OpenMP, they're finding bugs, and they do have code running. They expect most of the functionality to be available for HIP and OpenMP in the next release in November. And similarly, there is a SYCL DP++ port for the Intel platforms. And again, they have encountered compiler and runtime issues which are getting fixed. So access to this early hardware and early drops of software is very critical, both for this team and for the vendor, because it helps resolve those bugs. Yeah, next slide. Raja is a product out of Livermore, and it comprises 3 parts. The main Raja, which is C++ kernel execution abstractions. There's another library called Chai, which is C++ array abstractions, and Umpire is a tool for memory management. And Rajas, and all 3 of them are used quite extensively in Livermore applications. Almost all of the main weapons codes use them, and even the other applications at Livermore use them. And in ECP, they are used in SW4 in the EQSIM app, then in GOSX in the Subsurface app, and a bunch of other projects as well that are listed there. So they have full support for the HIP backend for the AMD platform since January, and that's been a key part of the El Capitan Center of Excellence activities. The SYCL backend is in progress, and it's running on the pre-Aurora systems as well. And there are many applications that have demonstrated significant performance improvement on GPU nodes on Sierra and the CTS platforms that are listed here. Yeah, next slide. Yeah, the other project that I want to cover is the MPitch effort, because it'll be the primary MPI implementation on all 3 of the exascale platforms via Intel MPI and Cray MPI, the vendor products on those platforms. This is led by Pawan Balaji at Argonne, and MPitch has been a key influencer in the adoption of MPI for a long time. and it is running on big systems for a long time as well. So their ongoing efforts are related to MPI forum and standardization, addressing key application-specific issues, a lot of work related to GPUs, and they're working with all three of the vendors there to make sure that the data movement from GPU memory happens efficiently, and work on non-contiguous data communication as well with GPU memory. Yeah, next slide. So they work closely with the vendors, Intel and Cray and Mellanox and so forth. And these activities include not just telecons and other meetings, but they have had week-long hackathons with the vendor MPI development teams. And this is a photo of, I think, with the Intel MPI team. They used to be in person, now they are happening virtually. So this leads to a lot of close collaboration and shared code, and features developed in MPitch immediately make their way into the vendor MPI and then appear on the system at the facility. They work with various applications on specific issues or specific features of MPI that may help that application, and that's shown on the figure on the left. And they're involved in various of the standardization efforts. Next. Yeah, this just shows recent efforts related to GPU support. So they're taking advantage of the GPU RDMA to transfer directly from data from GPU memory to GPU memory. They have developed a new, recently developed a new library called YAXA for derived data types that also exploits GPU memory efficiently and gives good performance on derived data types. So this is a very important issue right now that they have to do a good job on the GPU aspect of it. Next. There's a bit of a delay in the, yeah. And this is one last slide on this project, is that they've also done some improvements related to MPI plus threads or hybrid programming, which is also important in the area of making the locks needed more finer granularity. They have a new virtual communication interface within MPitch, so different threads can map to different VCIs, and thereby the concurrent communication from multiple threads can happen with fewer locks and contention for internal MPI resources. So they're getting much better performance now in the MPI plus threads model than previously. Next slide. Yeah, so
I think we should skip through these.
Yeah. So I have, you can quickly scroll through them. I have some leave behind slides, which are one-page summaries on progress on the other projects, which you can see. And in the interest of time, I'll hand it over to Jeff to talk about his area.
Thanks, Rajiv. Hi, I'm Jeffrey Vetter from Oak Ridge National Lab. I'm excited to tell you about some of the developments in ECP surrounding LLVM. But first, I'd like to give you an overview of our WBS element. Next slide. So 232 is development tools and compilers. It's really focusing on the complex and heterogeneous nodes that we're seeing emerge. Some even call it extreme heterogeneity is where we're headed. And so the idea is to develop the compilers and programming tools that help the applications teams and the other software technology teams be able to port these new complex architectures. Some of the things we're looking at include OpenMP, OpenACC, Fortran, and then other architecture-specific tools like performance counters and performance analysis tools. Next slide. The current portfolio is this. We have an SDK project as well, led by Bart Miller at Madison, Wisconsin. Exapappy for the performance counter API from Jack Dengare at UTK. HPC Toolkit is John Miller, Crummy at Rice. Proteus Tune is led by myself, and it focuses on OpenACC support in both Clang and Flang and the TAO system, as well as other enhancements to LLVM. Solve project, led by Barbara Chapman, is spearheading OpenMP and LLVM. And finally, Flang is Pat McCormick at LANL, and he is obviously looking at Fortran support in LLVM. Next slide. So I chose, instead of highlighting each project, just to take the theme of telling you what we're doing in LLVM, because we think it's a very impactful project. We think that there's a high probability that these LLVM improvements could last for decades after the exascale hardware is retired. And so it could have quite a long life. Next slide, please. So for those of you that don't know, LLVM is an infrastructure for creating compilers. And there are several benefits to this. The first is it's quite modular and has a well-defined IR that allows many languages to generate that IR, and then the downstream backends transform that IR to different devices or architectures. One key component of LLVM that's a real advantage in the heterogeneous world is that it has a very permissive license. It allows people to contribute. It allows people to take LLVM and import it and improve it and basically use it as a product. It's been used in many languages, including C, C++, Julia, Rust, Swift, TensorFlow. It's very popular. The backend infrastructure, again, allows the vendors to create, in some cases, proprietary backends that ship with their device, like a GPU, but the front end of the tool chain is completely open, and people can make improvements to it and work with that part. And the C++ front end and some of the other capabilities are state of the art. This is what many of the vendors are relying on today for their compiler front end. And it does have a large community. It has a review process and a standards process that is very frequent, very involved with that, literally thousands of people and hundreds of companies contributing to it. Next slide. So in fact, next week is the LLVM dev meeting. They have 2 of these every year. Normally there'd be one in Santa Clara and one in Europe. They're virtual now, of course, but these meetings attract, in some cases, more than 500 developers. And I'm happy to say that next week's meeting has no shortage of ECP sponsored presentations in it. And you can see everything in here, from the Flang update from PGI NVIDIA to OpenACC support in Flang with MLIR. Next slide, please. So what is ECP doing? So as I've described, LLVM is very popular as we go work our way from left to right here. The Solve project is looking at enhancing the implementations of OpenMP and LLVM, looking at things at how to provide unified memory support with optimizations, also prototype some new features of the spec in an implementation that can be implemented in the actual release of LLVM downstream. They also have done things like create an OpenMP test suite to track the implementation of OpenMP, to make sure that all the compilers that are providing those capabilities provide them to the standard, as well as track the performance of those to make sure they're performing well. The next project, Proteus Tune, is doing core optimization improvements to LLVM. I have an example of that in a moment. Also, they're providing an OpenACC capability for LLVM. And these include 2 front ends. One is the Clang front end that provides OpenACC, and the second one is FLAC, and that is OpenACC support in the new Flang front end. We also provide auto-tuning support for OpenACC and OpenMP. Tools from the University of Oregon, which are very popular and widely deployed. Next is Flang, and I'll say more about Flang in a moment, but as many of you know, Fortran is still very important in our community. And one of the challenges has been having a open source production quality Fortran front end that would map on something like LLVM. And so about 5 years ago, NNSA invested in NVIDIA and PGI to open source their parser front end that they had used in their Fortran compiler for years. And now ECP is continuing to fund that work to make it upstreamed into LLVM according to the standards and policies of LLVM. And now it's been recently approved by the LLVM community, so it is part of LLVM at this point. There's still much work to be done in the backend optimizations and runtime systems. I'll say more about that in a moment. HPC Toolkit is the fourth project that's working on LLVM. Most of their focus, since they're a performance tool project, has been focusing on the OpenMP profiling interface. They've been working both with the specification forum as well as the LLVM community to make changes and improvements there. And then finally, the ATDM project in NNSA has been enhancing LLVM on very specific optimizations like template expansion for things like Cocos and Raja, which we've just heard about, to try and get rid of those very long compilation times using things like just-in-time compilation. They've also been doing Flang testing and evaluation. And finally, the model here is that many of the vendors are using LLVM internally. And they basically do that by taking the releases of LLVM and then adding value to them as they import them into their company software stack. So they have a vested interest in it doing well. And you can see a list of the companies here that both depend on and contribute to LLVM. Next slide, please. So just a couple specific examples. The first one I picked because many projects are working on this Fortran effort. So Fortran continues to be a major requirement for us. In this diagram you see on the right, it shows you the layers of the compiler. Now you start with your Fortran program at the top, you parse it into an AST, you take that AST and turn it into an MLIR representation. Now, what's important to note here is MLIR wasn't developed by us, it was developed by Google, and it was recently included in LLVM, and it provides a higher level of abstraction to do high-level optimizations, things like multiple loop optimizations, function cloning, and things like that. What we're adding to that is first OpenACC dialect, FIR, which is a Fortran intermediate representation, and then helping with the OpenMP dialect there. And the idea is MLIR is a framework where you can develop these dialects and have them work together in this framework so they can make the translations and the lowerings and then be picked up and used on Clang or TensorFlow or some other front end. And so as you work your way down this stack, what you see is eventually you lower it to something like actually a GPU representation. And what you see on the left is SPIR-V or NVIDIA or AMD. And then it goes to LLVM-IR and finally into the executable. At some level there, most of the vendors have a private back end that they keep proprietary because it hides some of the architecture secrets they have in their framework and architecture. But everything else here is open and it's being made public to the community. Next slide. So the second project I wanted to highlight was OpenACC support in Clang, which is the C++ front end for LLVM. And this project started a few years ago because there really wasn't a production quality standards conforming OpenACC compiler available. And so we wanted to start mitigating risk by developing that. The way we did that was create a front end in Clang with support for the OpenACC directives. It parses that, creates a OpenACC AST, and then a key point here is it translates that into OpenMP, because there is already an OpenMP backend there. It takes that AST and translates it in memory to OpenMP, and then can either write it out as OpenMP source code that can be compiled by some other target, or to LLVM-IR and generate a executable directly from that. And so it's also making very good progress and should be ready in the near future. Ideally, Clang front end would use MLIR as well, but currently there are no plans to backport Clang to MLIR. But if that was the case, we could take that OpenACC and OpenMP dialect that I mentioned in the Fortran slide and basically move it over here unchanged and have it do those optimizations. Next slide, please. Lastly, we're also doing things that are important to a lot of people in the LLVM community, not just HPC. This is one example of a loop transformation that Michael Cruz at Argonne's working on to do speculative loop transformations. Now, what that means is in LLVM, you have this IR representation. You can literally make copies of it easily because it's just character strings. And what he's doing is using a speculation to evaluate the different profitability of different optimization sequences. And so what you see here is a representation where he would basically in parallel be able to make multiple optimizations, weight their profitability, and then choose one that it actually wants to generate code for, and then finalize that and feed that to the back end. And there are many ways you can generate the profitability heuristics, but that's for another talk. Next slide, please. So one final point, the ECP LLVM integration and deployment is we were asked to actually create a version of LLVM that we could deploy on our own. And this really addressed the question of what if some of our changes can't be fed back into the LLVM mono repo quickly enough. So for example, if we find major bugs in a platform and we need to get it in there for meeting our KPPs or for acceptance tests, for example, we need to have a plan B where we can basically compile and fix it on our own and deploy it locally. And so over the past 6 months, what we've done is create a very smooth process where on a nightly basis, we clone the entire LLVM mono repo, and then we have branches in that repo that ECP is contributing to. We have 3 now. Eventually, we'll hopefully have all of them in there. But the idea there is that if we need to, we will have an ECP deployment mechanism for the LLVM compiler from start to finish. And it does get mirrored every night. So if there are any merge conflicts, those get addressed on a daily basis. But we're benefiting from the hundreds of changes that are being contributed by the world, basically, to LLVM every night. And we do feedback. If you've used LLVM lately, you're using ECP software because it is making its way back in, and we have a number of people in the project who are in the top 50 contributors to LLVM right now. And so that's a very powerful thing. And overall, we have probably on the order of 12 or more FTEs focusing on LLVM work. And so there's a lot of effort going into this. And again, I'm excited about it because it could have very long-lasting impact both on ECP and HPC as well as the community at large. Next slide. So with that, I'll wrap up and answer any questions you might have of me as well as Rajiv or Mike. Thank you.
Thanks, Jeff. Thanks, Rajiv. Thanks, Mike. Questions for any one of the 3? Yeah, Dave. You're muted, Dave.
Good.
Hello, everyone. I love these big distributed efforts, but I always have to ask the question, how do you guard against malicious actors somehow getting in there? And obviously you're not going to tell us how to do that, but I want to be reassured there's worry about that.
Well, I can take a first stab. For not anyone, just anyone could get access to write to our software. In fact, there's pretty strong control. In some of the more advanced projects, even the development team themselves cannot directly commit to a repository. They do what's called a pull request, a merge request, and that request gets vetted by another developer and also has to run through a battery of tests before it can be applied to the primary repository. And that's the best practice. We see more of our teams adopting that, but there's none of the products that we talked about today allow direct access from anybody who's not within the project.
Right, and I would just comment on LLVM, even though it is this worldwide project, it has a vibrant developer community where all the changes are vetted very thoroughly, both for coding standards and optimizations and other features. And so you're relying on the community here, but there's some benefit in having that openness too.
I think Rich has a question.
Thank you, Dan. Nice presentation, guys. I have a question on the access to the ECP software stack and whether the source code and the Atlassian bug database and so forth are open to vendors and academics to increase their ability to collaborate with the program.
Well, first of all, the source code is all open source. Anybody can access it. In terms of reading it, right? They can't necessarily write to it, but they can read from it. So these are all open source tools. In terms of access to the database, issues database, we generally encourage our teams within software technology to have their primary issue database be in their product suite, not in the ECP Atlassian platform, because these issues are beyond, both in space and time, what ECP is concerned about, right? I mean, ECP cares a lot about the features, it funds a lot of the features. We definitely track activity, but we track it at a level of value proposition to ECP. And so we have JIRA databases that track lots of things, our regular quarterly activities, the KPPs, lots of things, but the day-to-day, detailed bug tracking issues are done in the team's repositories. And that's, I think, where it belongs. As far as access to it, I let maybe our program sponsor speak to that, but generally we give access to people, as business needs require. They're not generally open to everybody.
Martin, you had a question?
Thank you.
Yeah, one of the things I've heard about anecdotally is that the powerful levels of abstraction in C++ have led some developers to produce code that's almost compiler proof in terms of optimization and its complexity, and it results in a code that's perhaps easy to use in some ways, but is ultimately very cryptic. Have you met this problem, and have you taken any steps to sort of think about how one should deal with this?
Well, if you had a specific product in mind, I might be able to elaborate.
No, it's just I've seen. Well,
let me just say that our capability, our KPP3, protects against that to some extent, at least to some extent, right? It's because you have to do a sustainable integration of a capability in the stakeholder's environment. And if a stakeholder sees that the complexity of the software is so bad that it's not optimizable, that it's not usable, so we have to rely to some extent on our users' ability to assess products that we're producing. And so I would guess that if a user is paying attention, they would not incorporate in a sustainable way, at least, the things that we're providing. I can't think of at this point a product within our suite. We contribute to about 70 or so, where this is a known issue, at least in a broad sense. Certainly some require advanced C++ skills, but I think that is something that we need to expect of at least a member of most of our teams going forward. It's just it's the nature of how you program complicated devices, and now as we approach heterogeneous devices, even more so.
So let me chime in on that real quick, Martin. In the C++ community, this is just not our problem. A lot of people have this, where the compile times explode and the abstractions defeat the optimizations, right? And so one of the things that not only us but other people are working on is more support for just-in-time compilation, so that you know a lot more about what the parameters are when you do the compilation, and you can constant folding and things like that, and do a much better job of optimizing it. The other one is there are things like auto tuning and link time optimization that you can also benefit from, but that's a real trade-off. I can remember back to the late 90s when C++ came out and people were trying to figure out what should be an object, and they soon found out that they could really ruin their performance quickly by making a float an object.
Right.
One of the
Absolutely sure that you guys have taken steps to avoid that, but I'm just wondering if you had any sort of general principles that you were using to avoid it occurring. And it sounds as if you have safeguards, but not necessarily a kind of a set methodology. Let's put it like that.
Well, we're still, many of our projects are discovery-based efforts that that feed into a productive pipeline, product-oriented pipeline. So we have to allow some variability in approaches. Otherwise, I think we miss out on opportunities for innovation. I can say the existence of E4S and LLVM as ecosystems go a long way to protecting against bad approaches, ultimately unusable approaches, living too long a life, right? Because we have safeguards in place, because we do regular checking, are these teams making progress to integrating capabilities into the codes that need to use them? We can more quickly than in the past identify things that just aren't going well and make corrective behaviors as a result.
Sounds good. Thank you.
Sure.
So I have one of those philosophical questions that probably has no answer. And it's related to what, Roscoe and his team and all of you have been trying to sort through, and that's the ultimate transition, which is, the great thing about ECP is it's developed a really vibrant ecosystem and a large code base. The bad part about it is it's developed a large code base. And so as you think about maintenance, what do you think about the sustainability and balance, just given what will be an inevitable long-term support process with naturally bounded resources? And like I said, it's a philosophical question with no obvious answer, but just wanted to throw it out there for a little bit of conversation.
Sure. Well, I can start. I'm sure Jeff and Rajiv had thoughts too. One is, in a fundamental way, the L4 level of activity within ECP, which is all these individual ST projects, right? We have 34 of them. But their activities are not fundamentally different than what was going on before ECP. So a large bulk of the funding that DOE OSCAR is providing to ECP is the same money they've been providing for decades. Maybe in more variety or, but addressing problems of the day. The value add that ECP has provided are the SDK and E4S, which certainly cost money, but look at what they provide. They provide, I would argue, better, faster, and cheaper. They're allowing our development teams to feed into a well-structured software architecture, into a well-structured and managed software ecosystem that ultimately should provide better quality for their software, do it more quickly out to the users, and do it in a way that's cheaper than what we've done in the past. And I would argue that if you want to get better and faster and cheaper in the future, you should keep us going.
Thanks, Mike.
Yeah, I just had a quick comment, Dan. There's been a NITRD workshop on extreme heterogeneity the past few days. And one of the things that came out of that was this major concern that, now you're just not dealing with x86. You've got an AMD GPU branch and an Intel GPU branch and an NVIDIA GPU branch and FPGA branches. And it's quickly going to become a crisis because no one can support all and keep up all of those different versions of that software without some kind of model, right? And we're benefiting because it's open source, but you need some gatekeeper to make sure things are consistent and up to community standards.
Yeah, it's kind of the software version of the ASIC hardware challenge, right? How do you maintain state-of-the-art cadence? Yeah. All right. Any other questions or comments before we move on?
This is Roscoe. I'm sorry, I just came back in at the last end of that conversation, but I think what Mike was talking about and Jeff is very consistent with what we found in the transition report and with the recommendations we had. And it's something that came across very clearly in our discussions with ECP and others.
Yeah, if you want to save money, give us money.
Good answer. Yeah.
All right. Thanks, Mike, Rajiv, and Jeff. Let's move on to our last talk before the break. Ben's going to talk about ESNet 6.
That's right. And I want to do a quick audio check. Can you hear me okay?
Yes.
Excellent. And my partner in crime, Inder Manga, the executive director of ESNet, will be driving the slides, and we'll take the baton early in these moments together for this last session. I think this two-day meeting, I don't know if you're a baseball fan, it's sort of like we're at game 2 of a doubleheader, 4th inning, the grounds crew's out, smoothing the dirt, time to stretch, get a drink, take care of yourself. We'll be at the break before you know it. But first, we're going to do something a little different than what you've heard this morning. We're going to talk about ESNet 6. And as we approach this new era, the early finish date for the project will be honest before we know it, if all goes well, at the beginning of 2023. I wanted to thank the committee, to Dan and Barb and Christine, for giving Inder and myself a little bit of time to give you a glimpse onto a couple kind of intellectual planes of this enterprise. And next slide, please, Inder. So I just wanted to, some of you may be new to ESNet if you're new to the committee. I mean, many of you know ESNet, but what we're going to try and do is give something for anyone who's listening, something maybe that you haven't heard before in this presentation, because partly we're going to talk about where we are with ESNet 6. And since you last heard a formal presentation about ESNet, we've passed a major milestone for the project itself in achieving the critical decision 2.3 approval from DOE executive leadership, which means baselining the cost, scope, and schedule and beginning the project. And that milestone occurred in February. So talk about getting the board green and then having a pandemic hit you in the face. This team, illustrated here, does it all. They operate ESNet and have kept it humming in this incredibly challenging time. So part of this talk is also me taking the mic and celebrating their efforts, but also wanting to portray, as we're in the lead into ESNet 6, this new era, motivating the strategic themes of what that would be about. And the other thing I'll just note is I intentionally describe ESNet as a complex system. And that's something that I'll touch on more deeply in a moment. Next slide, please, Inder. So before I came to OSCAR 4 years ago, I spent a number of years really diving deep into the world of the Office of Science user facilities. And you can see I put a little glowing gold halo around ESNet. Now, ESNet is a very peculiar Office of Science user facility, and because it is essentially, in some stripes, essential infrastructure, right? We know that well. But it's also really a service provider to the service providers. So all these facilities deliver incredible science research platforms for a wide range of different types of science use cases. But inside the engine of ESNet is not just about moving bits, it's about understanding where science is going. And the way that ESNet as an enterprise is evolving as we approach the ESNet 6 era really is about that story. Next slide, please. So set your dashboard of your DeLorean to 1985. I'm going to take you back for just a moment as we look forward past the break to a sync up on where we are with the ASCAC 40th anniversary report. I went back to the archives, as any good student of history would, and looked at the beginning. And you know, when this report was published in summer of 1987, sometimes there are these things that, you know, that you see, they sort of jar you with how you could have ripped them from the past and plopped them down in the present, and they'd be just as meaningful. And this little bit of yellow highlighted text, which I'll read, the central motivators, mission motivation for ESNet at its birth were improved access to Office of Science scientific facilities, needed information dissemination among scientific collaborations, and more widespread access to existing supercomputing facilities. How things stay the same, right? What's profound for me in reflecting on this, is I wanted to share just a moment with you about, is this is an era where data networks didn't exist. So here we're motivating a change, a state change for science. We're going from the pre-era of limited transit of data to a working system. And what I'd like to motivate, just setting the table for Ender and the deeper exposition he's going to provide, is that I believe that we are at the threshold of just a profound transition for ESNet as we were in the mid 80s. That is, the ESNet that we knew, that we have known and enjoyed in its incredible performance, we are going to see a totally substantial change empowered by ESNet 6 and some other investments we're making. Next slide, please. So this is just a screenshot of what's tucked in that report from '87. Just a thumbnail sketch of, you know, how does this ESNet thing work, right? Essentially, it's you know, a wide area network that itself is a connector of resources. Very simple in some sense. So here you have, you know, connecting to the computing resources, connecting to the outside world, the internet, and here's connecting to your local area networks at laboratories. And if you go to the next slide, please, Ender. This model is essentially what we have today. So if you're a connected site, this is just a little pictograph of the famous science DMZ model, which provides a way of having huge data flows without fracturing your cybersecurity campus requirements. Essentially, that architecture has survived for decades. Next slide, please. And we call these connected sites site users. And this is a profound thing. And it's taken, sometimes you arrive at conclusions that are shockingly obvious, but it takes a while to really let them sink in. When I think of our site user partners, and in this Office of Science user facility context, of course, we have probably on the order of 100,000 individuals who depend on the network. But the institutions that rely on it are really the really deep partnerships. And up in the upper right corner of this slide, I'm kind of getting a nod to, if you're familiar with X-ray light sources, you know, those have also been around for decades and support the ability for an external partner to build a beamline. And they determine the fate of that beamline to a large degree. They're driven by their own mission to do that. And that's really the relationship that ESNet has with its site user partners, these connected sites. Next slide, please. I don't expect you to see any specific detail here, but basically the story is our partnerships are growing and growing and growing. And this is a good thing because it means that we are identifying science use cases and DOE mission drivers that are well vetted in terms of the mission need for ESNet to support their work. But it also means that there are burdens on ESNet that weren't there back in the beginning or even a decade ago. So you can see we've had a 50% growth in the number of site partners in less than a decade. Next slide, please. And that's something that we have to be mindful of because we are, the science mission of ESNet is sacrosanct. And so the ESNet 6 project itself, I want to just highlight one thing if you're not familiar with it, is that it is a greenfield build of a new wide area network. And this is a really, really profound point. That means that for the first time in its history, ESNet will have complete command essentially of the infrastructure on which the bits ride. And this map represents all the physical places on planet Earth where there's a build activity, and you'll get to see some great graphics from Ender in a moment about how the build of ESNet 6 optical system has proceeded in the era of the pandemic. Next slide, please. So wrapping up, I just want to have a few quick slides before I pass the baton to Ender to set the stage for what will be a deeper dive that Ender will provide and some of the investments that are going on now to prepare for the ESNet 6 era. The way that we think about really the themes of this moment in time as we are inspired by the past and bridging to a future of ESNet 6 revolve around foundations, the next generation infrastructure and services that ESNet 6 exemplifies, innovation, the test beds and advanced networking R&D that we need to position ourselves for the future. And something very interesting that I know those of you who are denizens of the HPC world will understand intuitively is co-design. And this is a really profound change for the ESNet team, in that it's engaging even more deeply and in qualitatively new ways to enable our partners' work in a very deep and embedded way. And Ender will provide some specifics to that. Now, what is this kind of medallion thing on the right? This thing sort of is my, simplistic PowerPoint-y attempt to sort of encapsulate the scope of the mission drivers today. I know this is a bit of an eye chart, but essentially we have all those user facilities in the DOE National Labs who depend on ESNet and that offer a lot of use cases for contemplating, as you've heard already in this meeting, and in the reports from Tony's subcommittee and Roscoe's subcommittee have recently provided, and the AI for Science town halls. There are enormous opportunities for the network and the computing facilities to integrate with experimental and observational platforms in new ways. We have the traditional R&D engine that is the ESNet testbed. It supports the nation's R&D community. And we have, and the little green box below, these just acronyms of major also science projects. So if you go to the next slide, please, Ender. What we're talking about here at a very high level is the following. When I think about foundations, the ESNet 6 architecture is about leveraging the investments of the OSCAR research community in the past and the wider R&D networking community to bring software-defined networking into reality in a wide area, continental scale, terabit scale network. And what this really means is if ESNet is the conductor of this orchestra of commanding its network, and if you follow me for a moment in this analogy, and this is a loose analogy, previous generations of ESNet or wide area networks means that you have, say, a cello section that can only play in C major, okay? Or you have certain just constraints on what you can do in terms of commanding how the orchestra behaves. And what ESNet 6 does in providing this greenfield build with all the knobs, all the players of the orchestra at your fingertips, it allows you to software orchestrate, to command the network in fundamentally new ways. Next slide, please. Hard to represent visually. This is a pretty simplistic picture, but essentially, this moment in time, Ender will get into this in much more depth, I won't dwell on it, is that the composition that Ender and his team have of the R&D portfolio that the ESNet team is involved in today, very strategic. That is, it's building not only the intellectual capital that we need to be ready for what might come down the pike, which includes not only next generation internet, the great work that Robinson and the field have provided in the 5G workshop recently, the quantum internet, but it's really about also having that intellectual expertise inside ESNet. And that's something that's very profound for all user facilities, is that you have to have that intellectual horsepower inside the enterprise in order to respond flexibly, capably, and nimbly to where the community needs you to go and where the agency needs you to go. Next slide, please.
Ben, I hate to interrupt, but is there any chance you could make your slides a little bit bigger? They're kind of small compared to what the other presentations have been. Those of us who are old geezers are just struggling a little bit to read.
Yeah, Ender, if you're having an issue, I can take the slide sharing.
Sorry to interrupt.
No, it's important to adjust.
It is impossible for me to see what you're seeing. So, I mean, I have shared the PowerPoint slide. I can share my desktop if that makes it easier for you, and see if that makes any difference. And I'll put this on play mode and see if does this help you at all?
I think the issue, Ender, is that you have an extremely wide screen monitor, and it's giving us black bars on the
edge.
Yeah.
Edges. Yeah.
Don't sweat it. I just, if it were easy, but otherwise just go ahead. The slides are going to be available afterward anyway.
Right.
I think this view is probably more comfortable.
let me just open up my laptop where.
Yeah, and while Inder does this, I'll just continue just on this third theme that we were on, which is co-design. And of course, many of you are familiar with what co-design means for HPC. It means this, this model, this mode of work that really exemplifies DOE's culture of team science, where you have projects, teams that self-assemble, typically computational scientist, a domain scientist, and they advance forward towards a goal that they might not otherwise be able to achieve because by virtue of being integrated together. That's great, Inder. I think that's much better. Perfect. This is the right slide. And so you'll hear about this more in a minute from Inder, but the Greta instrument, which will be deployed at the Office of Nuclear Physics' new, I think $650 million facility for rare isotope beams at Michigan State University, which will become the world leading center for isotope research and a lot of fundamental nuclear physics research. This is a really profound achievement in the last couple of years, where network engineers at ESNet have been embedded in the project team to develop the data acquisition system that interfaces. This will be the world's foremost gamma ray detector system at FRIB. And really what this is about is exactly what you know and love about co-design in the HPC world now in context of data acquisition systems, which have to interface seamlessly to the wide area network. Next slide. And I think we're just about at the, one more slide on a co-design example. The Vera Rubin Observatory Project, formerly known as the Large Synoptic Survey Telescope. Another example of where today the ESNet network engineers are working seamlessly with the project team in the project phase. It's not just about, hitching wagons together and connecting their data architectures and data repositories to ESNet. It's about a holistic approach to the design of the data management systems in partnership with the project team and our federal partners at NSF. So I think next slide, and that will bring us back to just a pause point where Inder will take the baton, but just to say thanks again for the opportunity to set the table, and take it away, Inder.
Well, I am not sharing. I think Hikmet is sharing. He took it over seamlessly.
Excellent.
So this is really wonderful coordination. So I really appreciate it. So if you don't mind, I will go next slide. Okay. So I'm going to start back again, take a little bit step back. Ben, really appreciate your input, and I hope you guys can hear me okay. The vision that we kind of operate with, or we live and breathe every day as a user facility, is the use of networks to accelerate scientific discovery. And this is kind of a vision that scientific progress will be completely unconstrained by the physical location of instruments, people, computational resources, or data. So we really, really want to make your science happen, whether you are in the US, your collaborators are out of the US, your instruments are out of the US or within US. And that doesn't mean we build a global network. And in nowhere in the vision is the word network put anywhere. So it is all about enabling and making the science mission happen. Now, this, next slide, this goal, discovery unconstrained by geography, leads to 3 pillars, which is our strategic focus areas or strategic goals. So of course, outstanding operations and planning. If you were not available 24/7, you would not trust the network. But then we need to create and disseminate information on how can science or scientists use the network in the most optimal way. And then we provide tools, software tools for that to happen as well. And the third pillar is looking forward, pioneering architectures, protocols, and applications. And if you do another click, it's a build slide that shows how it aligns with the 3 things that Ben talked about. So the foundations is about the network. The co-design is working on creating, disseminating information and tools, and innovation is actually building new things for based on our understanding of science and networking. Next slide. So if you were to drop off the call, these are the 4 messages I want you to go with. And I'm going to go through each one of them in more detail. First one is ESNet continues to execute well as a user facility despite COVID, and I'm going to show you some examples. ESNet 6 is a foundational platform, and I'm going to talk a little bit more about how we have deployed and what the architecture looks like. within the organization, there is a strong focus on innovation. And from 3 years ago, when I took over as a director to now, we have built a software and prototyping team that rivals the networking and operational team within ESNet. So we have grown to add that capability. And then network co-design, Ben gave the Greta and the Rubin Observatory example, is gaining momentum. And when you talk about new instrument and facility design, they are now working to build networking in at the instrument design phase rather than to be a bolt-on later when they have a data problem. So let's go click twice and let's go to the next slide. So once COVID hit, and this is an interesting graph in March, you can see this traffic only shows broadband service providers, and only 3 of them, I think Frontier, AT&T, and Comcast. Of course, Comcast is the biggest piece here, but you can see that from these 3 ASs, our traffic increased 4-fold. And that is kind of the transition we had to do. And it had to be seamless, and it was largely seamless for most of the sites. The only problem some sites faced was that their VPN licenses and VPN capability did not match the kind of traffic that the users wanted. So they were calling the vendors to get more VPN licenses. But the network itself, in terms of capacity, transitioned this seamlessly. Another click, please, on this slide. So when we talked to the NLCIOs during COVID, they said, my God, the problem we are facing is that people don't know how to build capable home Wi-Fi networks. So we need some help. So what we did was we have an informal home network Slack channel where we discuss tips. So we accumulated all our best practices and shared a 3 or 4 page document with all the NLCIOs on how people can configure their home networks, what are the tips, how to debug things. And that was really some help that all the ESNet engineers did as a volunteer. Next slide. Now, Barb did tell you yesterday that we saw a dip in traffic, and from the peak to the trough, we see a 30% drop in traffic. But on an average, for a 12-month average, we see an approximate 18% if we took average of all the pre-COVID and the post-COVID traffic. We believe the reason is that people are not at the sites, users are not coming to user facilities, they're not flying to the user facilities, and that's what's causing the drop. But in terms of the percentage of traffic, in terms of how much traffic is IP, how much is sciences, and how much is some of our circuit traffic, they seem to track. So we feel that all the science that can happen or data that can be moved remotely is being done, and that has not come to a stop. It's only things that require physical presence have contributed to this dip in traffic. And we think as that gets solved, this will come back as well. Next slide. Now, we are a distributed organization, and for 3 years in a row, we kept getting operational reviews which said ESNet staff are, have a workload that will lead to burnout. We need to hire more. So we have really taken that recommendation to heart. So since FY20, which is October 1, 2019 to now, we have hired 25 people, and 15 hires have been since March 1st, which means that we have not shook their hands or seen them in person. And I would say that the last 10 years of ESNet figuring out how to run a distributed remote organization has really helped in this hiring and onboarding of employees. Now, we have had people leave. So 4 people have left over the last year, including of which 2 of them have been retirements. We do have a strong student mentorship. We can't afford to get more students in terms of mentorship time, but we always get 4 to 6 students every year. And we had 4 students this year as well who joined us remotely. And right now, ESNet is a total 87 employees. So 3 years ago, when I took on ESNet, we were around 43 to 44 employees. So we have almost doubled in the last 3 years in terms of size. Now, I just want to say that it's not just quantity, the quality of staff seems to be excellent. So one of the awards we got in earlier this year was there is a holiday hack challenge by SANS called KringleCon. And our team participates all the time. So our team, Dob, Sam, and Vlad, which is our security team, actually won this award. Now, if you see in the middle, there are 3 awards. So they have won 3 first prizes last 3 years in a row. So this year, when they put the entry, they said, hey, there are 20,000 people that play this game. We do not want to be first again, so please give the first prize to someone else. So SANS created a special award called Extra Special Noteworthy Exemplary Trophy Award to give to us. If you do one click again, and if somebody didn't notice, it stands for ESNet, Extra Special Noteworthy Exemplary Award. So they create a special award for ESNet, which they're going to continue to give for the years to come. But that is what our team won. In addition, I don't know, Vint may be familiar and Wendy may be familiar with MRTG. I used to really not like those MRTG graphs and the way they display network information. So we invested a lot in building a traffic portal with the latest kind of GUI code and representation, and that is open source. And that is a finalist in the 2020 R&D 100 Award. And so we're happy about that as well. And by the way, this picture, which you see, shows 2 data transfers of around 1 petabyte each between NERSC and Oak Ridge. And in the middle, the reason why you see a gap is because there was maintenance going on the data transfer nodes. So they shut off the data transfer nodes. And as soon as they turned it on and brought it back into service, the data transfer started again and finished seamlessly. So this is to kind of show how the network can contribute, almost moving around 1.8 million files of 1 petabyte in this time frame, around 80 gigabits per second sustained. Next slide. So I'm going to move on to ESNet 6. Next slide. So the whole ESNet 6 architecture is to build a capability to deliver terabit scale performance with programmabilities. So the way we do it is we process the packet once at the edge, and we may do many things to it. We have a programmable data plane, we have compute at the edge to provide network functions, we have a service edge router. But once you have processed the packet, we really don't touch it again, and we send it through segment routed tunnels all the way to the end where it needs to go. So that is kind of the architecture which we call the hollow core architecture, where in the core, it is all about heavy speed bits. At the edge, is it all about processing and services that we can offer to our sites. Now, of course, we are investing a lot in software, both in terms of orchestration and automation, which are 2 separate things, as well as monitoring and measurement. And we'll get to that later. Next slide. If you look at it in a more traditional layered diagram that you see the internet, we have building the optical core. So we are building our own greenfield optical network, including amplifiers around and around 15,000 miles of fiber, 300 plus sites that Ben showed, building a packet core, and what we call the low touch path service edge. This is essentially traditional IP routing. But we are also building virtual network functions and something called a high touch path to provide even more variety of services. And this high touch path is something I will touch in my innovation section when I get to that. So this is what, in a very broad sense, the layers of the ESNet network look like. Next slide. In terms of timeline for the project, it takes almost as many years to build the network as it to operate it before you have to start building again. So I have told Ben that the CD4 date is actually 2025, early finish is 2023, but as soon as we finish CD4, we will start building ESNet 7 again. So that's kind of how it takes. So right now we are in the 3rd quarter of 2020. Our optical core build is almost done, and I'm going to talk about that. We are carrying a lot of our production traffic on our existing network. We have made a decision on which router to get, and we are starting to get the first routers in the lab in a few weeks, so we can set up the automation and the installation processes to deploy it in the next year, so we can replace the existing ESNet 5 routing platform with the new one. There are some project delays due to COVID. I think we are running around 3-month delayed, but we are also, given staff mental health and some stresses of the COVID era, looking at taking some of our schedule contingency and giving a little bit bigger runway so we don't make mistakes. I mean, we don't want unnecessary downtimes for customers, so we want to make sure we do things in a careful way. So, and we are still debating what's the right set of schedule delay to do while still keeping within the cost and the feature set that we have promised to deliver as part of ESNet 6. Next slide. So this is what the status looks like from an optical network. OLS stands for optical line system. Most of the phases are complete. You can see phase 4 was accepted in line 17. The process is the vendor we have contracted with builds the phase. We then test each and every link and we accept it. We need to make sure the optical losses are consistent, what we want and everything like that. There's 6 phases. The 6th phase is going to Brookhaven, which is targeted for next year for a variety of reasons that I don't want to get into. Now you see some sites marked with additional COVID-19 access constraints. So some of the national labs, for good reason, had constraints on how much we could do. And some of the sites like in New York, the co-location site had issues. So we have things to be done there to really accept the whole network. And we have marked those as things that have caused us a little bit more time and more communication in order to make that happen. Next slide. So this gives you a view from the network management interface. So this is alarm view. So as the optical network was bringing up, you could see the alarms disappearing and things becoming green. This build happened right within the COVID time. So 300 amplifiers, 29 hub sites were installed between April 28th and August 19th. And that whole this whole substrate was built with, a lot of coordination and communication with our vendors. Now, I do want to say there was a delay. Our real ideal date was to be done before August 10th, our original date. And we slipped by a few days for sure, but I just want to give kudos to the team, which has worked really incredibly well, and our vendors, to make this happen. So this is just an animation which keeps going again and again. It has different snapshots as things came back online. Next slide. Now, the way I say about building the network, and please watch this animation as I speak, is it's 2 train tracks. We have a train running on one track at full speed at 100 gigabits per second or more. We have another train that we are building on the second parallel track. So what you see here is we are transferring customers from one track to the other as we are building it. So we were decommissioning the existing network and moving traffic to the new network as it was being built, parallel to as the new optical network was being built. So this shows you kind of a timeline from, like you can see the dates on the top, 8.1, 8.4, 8.5, as we transition the wavelengths from the existing network to our ESNet 6 network. Now, 75% of all production traffic is now on the new optical network. And because of the stress and some mistakes were being made and because of some issues with COVID in terms of getting access to the sites, everything was not transitioned. The rest will be transitioned by November 20th. So you can see, okay, it's hard. So the animation repeats itself, so I'm sorry for that. But you can see around the West Coast, there is a small portion on the Northwest that still needs to be transitioned to the new optical network. And that goes with the acceptance of that phase was done in September 17th. So we are still to September 24th. So we are not transitioned all the services there yet, but by November, we should be all done. And we should be running on the new optical platform. Next slide. Before. So this is just a projection of FY22 where we'll be. And you can see the dark lines represent around 1.2 terabits per second. So there'll be a mix of 800 gig to 1.2 terabits per second initial capacity deployed in this whole terabit network. And of course, we have capability to do a lot more since we have access to a lot of spectrum on this site, so we can add more bandwidth as science continues to grow and as data continues to grow. For most of the network, 400 gigabits per second will be our base wavelength capability. There are some spans that are longer, which will be 2 by 200 gig waves, but most of the network will be 400 gigabits per second waves from 100 gigabits today. Next slide. By the way, any questions? I mean, I can stop because I'm kind of doing phase changes from topic to topic. If there are any questions, I can take them on ESNet 6 right now. I can't read my chat, so if there were questions, I missed it.
How much more do you have to go? I just asked because that'll determine whether we pause for questions or continue.
I do have 10 more minutes for sure. If you don't mind, we were running late before and I...
I recognize that. I was just trying to understand whether the pin-up questions. Maybe we should take a few questions now. I know Vint has a few about the network.
Well, thanks, Dan. Inder, this is a wonderful presentation, and I'm all excited about where you're headed. You used the term hollow core, and I'm assuming that was metaphorical, but the reason I'm asking is that David Payne at the University of Southampton is actually making hollow fiber right now in order to reduce latency by transmitting through the atmosphere, as well, through air rather than through glass. So you weren't literally meaning hollow fiber, were you?
No, I'm not meaning hollow core fiber. What we are talking about is basically segment routed tunnels where the tunnels are carrying the packet information.
It's like an MPLS thing where, so it's like a 2 or 3 hop network instead of a hop. Yeah. Second question is whether the optical design that you currently are implementing for ESNet 6 is capable of carrying both conventional and quantum photon communications.
No, the current one cannot carry quantum photons information as far as I know, because it requires single photon. Now, it is some of the research that needs to be done is, so right now you send a lot of photons and you amplify them at everything. One of the things about quantum thing, especially in a QKD kind of network, is you send single photons and you have single photon detectors. And that just requires a different path. So if we can take spectrum and we can have equipment that breaks that spectrum out and there is no interference between spectrums, then definitely this can support it. But one of the things that I have been talking about is for quantum is that you do need a parallel fiber infrastructure to the conventional infrastructure, especially because conventional networking provides the control, management, and the key pieces of information to be able to transmit information without breaking Shannon's law of information at the faster than speed of light. So you need the classical network working in concert with the quantum network to make the quantum network happen.
Fully understood, not a problem. Last question about the transition from ESNet 5 to ESNet 6. While you were moving the ESNet people off of ESNet 5 fiber onto ESNet 6, do the interfaces still all look the same? It's still the same switching gear and everything else. So that part is transparent to most of the users.
So what we did was, yes, we're doing it in 2 phases. We didn't change the router and the optical at the same time because that would be very disruptive. So we kept the same router so they didn't see a difference. We moved the waves.
Yeah, okay, thank you.
And now we will work on the routers, which will be a little bit more disruptive and require more careful coordination.
Amen to that. Okay, thank you very much, I appreciate it.
Back to the presentation, please, or I can do it.
Oh, let's see, are there any other questions on the transition just before we go on? Okay, go ahead, Inder.
So my next focus is going to be on innovation, and let's go to the next slide. So the one thing I talked to you about was high touch. And this actually is a very interesting approach that we are trying with. It's in the lab, it's in prototype phase, which is integrating edge computation, storage, and smart NICs. And what we want to generate is services that are not available commercially. So I'll give you one example. We are working on something called packet scope. I know the slide is small. I apologize. I tried to cram a lot of information in this. But packet scope, let me tell you a thing. When we talk about existing commercial routing equipment today, when we get telemetry from the network, we get what you call that flow information about network flows. We get samples. We get 1 in 1,000 samples. And we said, why can't we get information on every packet that's going in the network? Why don't we build what you call a packet scope, like an oscilloscope or a telescope and for packets? And so what we have built using FPGAs and compute, and the FPGA work is being done in Berkeley, and you see the architecture below, is an ability to take any flow in the network and get packet telemetry on a per packet basis. And then now what we are building is applications that say, hey, this flow is not getting the right performance. You put the packet scope on, dynamically configure that flow to be looked at by the scope, and be able to say, hey, and you get real-time visualization of the data throughput and say, is the good put really good or bad? Is it getting lost? Why is it getting lost? Where is it getting lost? So you can do that, and that is something in the lab, and we are writing papers on that right now, but it is a combination of research and advanced development and engineering that will be deployed on ESNet 6. And this is kind of one of our most far-reaching, most risky parts of the project because it's innovation, but it is something that we're committed to delivering as part of the project. Next slide. Now, there was a SENSE project, which is SDN for end-to-end networking. And the problem we were tackling there is that when it comes to moving traffic, it is actually moving from the data transfer node at the site or the instrument to the other side. And no matter how good we did traffic engineering within the network, if the end sites didn't have any control or required manual intervention, all the automation in the core of the network was of no avail. So we had this ASCAC research-funded project called SENSE that has now become part of XFEL, which is an ECP project to move data from LCLS to NERSC for processing around terabits of data stream eventually, but they're working on that right now. And also this project is being taken on by the high energy physics community as part of their high luminosity LHC experimentation and their desire to move 400 gigabits per second data from Europe to US. And so we have taken that core research project and turned it into as an innovative research project. And what we are doing is automating the configuration all the way from the NIC on the server through the network to the NIC on the other server. Next slide. Now that we build an intelligent edge with a high touch service, there is another opportunity. The opportunity here is to take the SENSE project, the high touch project, and provide data transfer as a service. So there is another experiment that is going on taking some of the data transfer nodes, containerizing it, and offering containers as a service so people can deploy data transfer protocols of their choice and not be limited to a certain small set of data transfer protocols. And since we are deploying it on our network, we can go from our edge to the other edge of our network without requiring the end sites to make changes or the end site administrators to learn new protocols or new way of doing things. And this is another research project in progress. Next. Now, one of the things we thought about, and this is something I want to talk about, is when I used to go to any Starbucks or go to work, I drive for an hour. So, you know, from in the Bay Area, I would always look at Google Maps to see what the traffic looks like. Or if I'm going to a Starbucks, when are they busy? When are they not? So I said, why can't we build a prediction for the network capacity? Can't we know in 6 hours is the network going to be congested or not? Is this even possible? So we had an early career researcher working on AI and ML for networks called Mariam Kiran, and she started looking at this problem and came up with something called a net predict, which is a deep learning model on how we predict, you know, few hours in advance what the traffic will be based on what is happening in the past. Now that's a really hard problem. Next slide. And this net predict model is right now in a GUI. Now, you know that network engineers never trust anything which is ML AI. So what we have is a dashboard, which is kind of to build trust. It's a real-time ML performance. It is using the same data and statistics from the network that you saw in the portal, but it is telling them and giving them predictions on available paths and less congested paths at what time between any source and destination site. And it is just to help right now build confidence that the prediction really works, and if it works. Now, there are some implications with prediction is that if you really send the traffic there, you have to continue learning. So you can't train once and use often. You have to have a model in which you continue taking feedback and almost like reinforcement learning, where you continue learning as the data keeps refreshing and as new traffic comes in or decisions you make may change the predictions of the future. Next slide. What we really want to get to is to get to this data, take this net predict and make it a more intelligent traffic engineering controller, so we can traffic engineer big data science data flows or elephant flows more appropriately. And that's also some work which is going on, which I'm very excited about within ESN. Still long time from deployment, but really interesting. Next slide. And the last thing I want to talk to you is BBR V2. This is not innovation at our end, but we're doing evaluation. So we had done evaluation of BBR in around 2016 timeframe, working with Matt Mathis from Google on how can BBR be used for high throughput, long delay product TCP transmissions. And again, we anticipate in the future there will be small buffer, high buffer delay product environments, and that'll and that requires a new protocol. So with BBR V2, we are excited, and we have just started a project internally using the 40 gig data transfer nodes that we have deployed to build a testing harness so we can test it and prove it out for high throughput data transfers. So that's other work that is going on within ESN. Next slide. So I just want to finish this innovation section, and obviously didn't talk about many things, other things that are going on within ESN, is that we continue to do advanced testing, research, and development of new tools and techniques within ESN. And we see that as a strong component of our user facility and for us to be relevant as the whole ecosystem around us evolves and changes. And that is something we really do, I really do take care of and invest in and want to continue to invest in. Next. The third thing which is starting off a lot is something called co-design. So we are being built into projects or brought into projects as a defined project. So one example that Ben shared about, and I want to go into detail, is that we got pulled into the development of the Greta data pipeline, and Greta is an instrument both in the network and the fiber design of the instrument. So this is nothing to do wide area network. This is networking within the instrument, going from filter boards to the event processing cluster to the event builder, so that the events can then be built and then sent for across the wide area network for other collaborators. So if you do a click again, so we develop the forward buffer, one click. If we develop the forward buffer architecture, and that was written in Go, and it is our prototyping and testbed group engineers that build that. So we could take raw data coming from filter boards, put as UDP, and then buffer it and convert it into TCP packets and send it to the event processing cluster, and do it without losing a single packet or reordering a single packet. As well as, now the good part is this instrument is network ready. So if that event processing cluster moves from close to the instrument to a supercomputing center far away, this whole architecture will still work. And that is, I think, what is important of the co-design benefit that the instrument gets. Next slide. And not only that, they had an issue. How do we fiber this instrument? So we worked on a fiber plan on how to get fiber from the instrument to patch panel so we can get the data out of the instrument. And that's also something that our network engineers worked with the instrument to design. Next slide. So I talked about the FPGA piece, and part of the co-design is happening is once we started doing the FPGA for our high touch project, we realized that there is so much space in the FPGA that we could put compute and DSP in it. So we are working with the ALS, and it was very interesting to hear Tony talk about instrument to edge, because this is something that we were already working on without knowing that strategic term, on how to incorporate DSP processing, event filter, and data transfer nodes into one box. And we are working closely, if you do with next slide, with advanced light source and NSEM to put these this edge node architectures, which we actually developed for our high touch in ESNet 6, but more use it for scientific processing with around 80,000 DSP cores and 1.6 terabits per second Ethernet IO in each of these boxes in the, that we are deploying. This was so exciting to our FPGA vendor Xilinx that they gave us a gift of around 48 FPGA cards, which we are again using to deploy. Now 48 FPGA cards means 480,000 DSP cores and 9.6 terabits per second capability, but we are using that to do the instrument edge computation. And this is a project, again, that is being done in collaboration with Computational Research Division within Berkeley Lab. And that's why I have their logos in the previous slide and this slide as well. And we are very excited about this co-design as well with ALS and NSEM. Next slide. The third co-design we're doing is working on a caching platform with high energy physics, CMS, and Atlas. Now, on the left-hand side, you see 3 cache deployments at UCSD, Caltech, and ESNet. And this was something we did in early May this year. We added a cache at the ESNet point of presence in Sunnyvale. And since then, you can also already see around 1.5 terabytes a day, or 3,500 accesses that day. We are still doing data analysis on how effective the cache is. But if you start thinking of the cache or a CDN for science, you can think even in Europe that 500 miles is one whole country. So you can almost put a cache per country and really optimize on how much network bandwidth gets used as you move into the high luminosity LHC era. And if you do another click, it shows that this aligns well with the data lake architecture because the data lake architecture just depends on caches. So this is another kind of a co-design project that we are doing with high energy physics that will really help, maybe something that we can bring to other sciences like climate and other science that have got data repositories that are distributed. Next. So I just want to kind of close with the 4 key points. But like any good book, there is an epilogue. And I want to get to the epilogue as well, Dan, if you can give me 1 or 2 more minutes. If you click on the next slide. So the first epilogue is that ESNet is supporting DOE and the National Strategy on Quantum and 5G. We have helped enable the testbed in Long Island, where there is a lot of quantum repeater testing going on with Brookhaven and Stony Brook. And we are in the process of working the Fermilab and use some of the ESNet capabilities in the Chicago area. We were part of the quantum blueprint effort in February this year. I was one of the co-chairs of the committee, and we participated in that session, helped write the report, as well as we participated in the 5G enabled energy innovation, which was run by Robinson and Office of Science. And we continue to contribute to the forward-looking strategy for DOE and the nation. Next slide. And the last thing is that NSF mid-scale infrastructure, they created something called Fabric, which is basically a terabit testbed nation scale to kind of help us generate new ways of using the network, new internet architectures. And the ESNet 6 architecture is being leveraged to design Fabric. And not only that, ESNet 6 footprint is going to dedicate some ways for Fabric, and it is being built on ESNet 6. So we hope with this NSF collaboration, we revolutionize internet architectures to provide a really at-scale network for network researchers at every university within the US. I have to say that right now, at-scale infrastructures are available to a few, like Google, Facebook, Amazon, Microsoft. And the network research community doesn't have access to those unless they join those companies as researchers. So what we wanted to do was team up with NSF and provide that research capability to really make sure that network research stays healthy in this country going forward. That's about it. Thank you.
All right, I think Bent had another question, and then we probably need to move on for just for timing reasons. But thank you, Ben. Thank you, Inder.
So this is just one last question for Inder, is whether the BBR-V2 guys have also looked at the QUIC protocol coming out of Google.
So QUIC protocol, yes, so QUIC protocol is coming as more at the browsers and end clients, and BBR-V2 we think is more for the high throughput stuff. So I'm sure the Google guys are aware of that, but whenever we think of QUIC, we think more of handsets, browsers, and making that better. But BBR-V2 we are looking at for multi, and making sure that it doesn't react badly with existing TCP cubic streams as well.
Got it. Thanks. No, terrific presentation, by the way. This is all very exciting. I'm going to follow up with some other stuff, so watch for email.
Okay. All right, looks like Tony wants to get in one last lick here.
Yeah, I was very excited by your instrument to edge architecture work, and I need to find out more about that. So
sure, we'll happy to do a presentation.
Thanks very much.
All right, thank you both. Really appreciate it. I know we're running a little long here. Barb, do you want to?
Oh, yes.
Do you want to do that video now?
The video, I can tell you, is 12 minutes long. It was when I looked at it. So yes, if people want to use their break and watch the video for Lucy, I think we can go ahead and do the break.
Then do it right after the break, maybe. I realize that's going to slide everything later.
Let me see if Christine has any concerns.
Okay, then why don't
I
we?
didn't know yesterday, but if we play it during the break, then people have the choice.
Yeah. So maybe come back in 20 minutes instead of 15.
So at
Ooh, how about, is that 2 o'clock?
yeah, that sounds reasonable. All right, so 2 o'clock Eastern, and you'll show it then, or I'm just trying to make sure I understand.
Well, no, I think what we're going to do is have Hickman go ahead and start showing it now.
Okay.
And
all
show
right.
it during the break. Yeah.
And we'll resume the meeting at 2 o'clock then.
Right.
We start by saying, let me, now I get it on the record. Let me say congratulations on your new appointment. Very well deserved. And we look forward to your presentation. So the floor is yours.
Thanks a lot, Dan. I appreciate it.
So feel free to go ahead and start whenever you want.
Okay. I'd like to take this opportunity to thank you, Dan, and Barb, and the rest of the Oscar office for this great honor to be one of the Distinguished Scientist Fellows this year. And as Barb mentioned yesterday, this honor comes with some sponsorship for 3 years. And so I'd like to take the next 30 minutes or so to describe my plans for this work. So what I'd like to do is to construct a framework, software framework for in situ reduced order surrogate modeling for direct numerical simulation of turbulent combustion at the exascale. And so as you know, the last 15, 20 years has been this march towards ever increasing faster supercomputers. And with that, we've been very successful at simulating larger, more complex turbulent chemistry interactions in DNS. But we're kind of at a juncture now where the machines are heterogeneous. They have lots and lots of different types of compute resources on them, including tensor processing units on Summit. And so it's possible now to start thinking about doing more complex workflows, including on-the-fly learning, deep learning, and reduced order model construction. And so that's what I would like to focus on in this project. So just a few words about my background. I've spent my entire professional career, 30+ years, since I finished my PhD at Stanford back in the late 80s at the Sandia Combustion Research Facility. It's a wonderful place. It's not in New Mexico, it's in Livermore, California. And it has been designated as one of the DOE's basic energy sciences collaborative research facilities, founded during the Carter administration when we had the oil crisis in the late 70s, and ever since been dedicated to energy science and technology for the US. The keys to the CRF's success have been this singular scientific purpose, and the work this encompasses goes all the way full spectrum from really fundamental work in chemical physics and chemical sciences at the molecular level to what I would call my work in the continuum level, where we've combined transport effects, turbulence, and chemistry interactions, and then on up into applied work supported by the Vehicle Technologies Office, more applied energy offices. And those have an arm reaching out directly to US industries, the automotive industries, GM, Fords, GEs, and other companies. And so it's nice to have under one roof these extremely strong ties to the application from the fundamental science and to the energy impact overall. As a collaborative facility, there's a very highly vitalized visitor program with hundreds of visitors from academia, other national laboratories, from industry around the world that spend anywhere from a few days to a sabbatical at the CRF, working side by side with the researchers. And so it's been a wonderful place to work. Next slide. So I'm a firm believer that combustion is still going to remain the predominant energy source for the country, and that transportation, largely owing to its high energy density compared to other energy sources, and that transportation, both ground as well as aero, will continue to depend on internal combustion engines for decades to come. This is despite the expected growth we're seeing in electrical vehicle sales and electrification of vehicles. But the passenger fleet will be dominated by IC engines in the coming decades. And you can see that clearly from a 2019 International Energy Outlook plot showing for passenger vehicles the breakdown into those that are powered by combustion, the diesel, gasoline, and natural gas, versus the battery electric vehicles and the plug-in hybrid vehicles. And so by the overwhelming amount of combustion from these vehicles, combustion will be the predominant source for energy for these vehicles well out into 2050. As such, the Vehicle Technologies Office has created a partnership in advanced combustion engines with the acronym PACE. And it focuses on resources across 6 different national laboratories in the DOE complex on common key barriers to engine efficiency. And so this is an R&D program that really seeks to try to make engines much more efficient and therefore reduce the amount of CO2 that's produced and other harmful emissions. And so the VTO office has leveraged OSCAR investments, in particular in high performance computing, and several of the codes through the Exascale Computing Project, and also recent advances in machine learning and AI, in order to understand some of the underlying research issues with making efficient, clean burning engines that would provide predictive models and a direct path to the industry OEMs and their CFD workflows. And so I think there's still a lot of work that Office of Science can do to help provide not only fundamental knowledge, but also help US industry. Next slide, please. And so in the last 10 years or so, starting from the Exascale Computing Initiative through the current Exascale Computing Project, I've been fortunate to have a team of from different national labs and universities to develop a combustion high fidelity suite of codes known as PALE. It ended up being called PALE because the co-PI at the time, John Bell, and I are both parents of soccer kids, and Pele is also a Hawaiian sun god, so combustion god. So that was how it got its name. But this is a suite of reacting flow partial differential equation solvers that feature block structured adaptive mesh refinement. And we've added multi-physics to these capabilities, including sprays, soot, transport, generation, as well as thermal radiation. And with the help through co-design processes with computer scientists and applied mathematicians alongside domain scientists like myself, we've been able to get very good scalable performance and portability on Summit and now on some of the test beds, Tulip and Iris, in anticipation of the arrival of Frontier and Aurora in the next few years. And so this has been a fun project, an ongoing one. And our challenge problem, our holy grail when Frontier comes up, is to be able to address key questions around compression ignition engines. For example, what is the distribution of reactivity in your preparation of a mixture, and how many multiple injections? What are their durations? What are the fuels you put in order to shape the right reactivity gradients in time and space that affect how ignition and subsequent combustion and subsequent soot generation occur. And so what are the and then furthermore, what are the rate controlling reactions? Can we drill down, which we can afford to do in simulations that you can't afford to do in experiments, given the adverse environments that these are conducted in at high pressure and high temperature? What are the rate controlling reactions that could possibly expand the operating map for these future engines? Now, in this work, we've leveraged heavily the chemical kinetics research at Argonne and at Sandia that has been supported by the Basic Energy Sciences Chem Physics Office. And they're generating, these chemists on our team, led by Stephen Klippenstein at Argonne, are generating automated combustion chemistry that's theoretically derived, UQ tested, and able to drop in accurate mechanisms in our CFD. Next slide, please. So we're very excited about the prospects of applying these AMR codes to real life problems. A second code that I've developed at Sandia over the years is called S3D. It solves a compressible reactive Navier-Stokes energy and species continuity equations and uses a higher order finite difference method for both spatial differentiation as well as for advancement in time. And it can treat detailed reaction kinetic and molecular transport models. We've been able to simulate turbulent flames and ignition with up to about a little over 100 species that we transport running on Summit, a good fraction of Summit. And it also has capabilities for particle tracking. So we can have tracer particles, we can have active spray particles that are fully coupled back to the gas phase and the liquid phase, and also soot particles. More recently, with the help of computer science expertise from Kwan-Lu-Ma and from other groups, we've been able to also include in situ analytics and visualization. I should say we've done a lot of analytics topological work in the past with Timo Bremer and Valerio Pascucci, supported by the Oscar office, and visualization work for both multivariate fields and particles with Kwan-Lu-Ma's group. And a lot of the data management work in the past has been done with Scott Klasky and company. And so this code capability has been a result of co-design all along. We just didn't call it co-design at the time, through these detailed interactions and collaborations with computer scientists. The code has been refactored a bunch of times, from MPI code to OpenMP to OpenACC, and more recently using Legion, a dynamic task-based programming model that is aimed at some of these more difficult to program heterogeneous accelerator-based architectures. Next slide. So as I said, we've been kind of chasing Moore's law, akin to the tornado chasers, right? We chase computer flops. And so because of the scalability and portability of the code, S3D, we've been able to take advantage of the growth of supercomputing back from the mid-90s, when this approach was only able to include one-step kinetics, global step kinetics, in a two-dimensional pseudo-turbulent flow. And if you follow this trajectory on this log scale of the computational problem size versus time up till today, I guess it's not all the way out to 2020, but we're now able to simulate full up laboratory scale flames with detailed chemistry in full three-dimensional turbulence glory. And so this is quite an achievement, and it allows us to really sit down with experimentalists and design experiments, both computational as well as physical, and make direct comparisons and also validate diagnostic techniques that may not be able to resolve all of the scales or only be a two-dimensional or one-dimensional diagnostics that miss information out of plane. So DNS allows you to do all of that. And same thing with measurements of the velocity field using PIV, and that's often has noise on it or is gappy. And so DNS side by side can help maybe develop methods to correct for some of this. So anyway, it's been exciting to be able to perform DNS on some of the largest machines that DOE in the LCFs have offered. Next slide. But to move forward beyond to exascale and eventually to yottoscale, we're still plagued with the problem of the fact that real fuels that are used in aviation or even in diesel trucks are described by chemical models with very, very high dimensionality. And so this plot on the bottom left shows the number of elementary reactions plotted on a log-log plot versus the number of species, where hydrogen, the simplest fuel, would be down at the bottom left origin, and the most complex fuel would show up, say, methyl decanoate, a biofuel, a biodiesel fuel, at the upper right origin, where one would have to transport tens of or thousands of species and 10,000s of elementary reactions in a CFD code, which is just not feasible even as we push out further with high performance computing. So the holy grail here is to find a low dimensional manifold in the composition space, species temperature space, that serves as a surrogate for the full system dynamics of the reacting flow. And this would allow us to then reduce the number of species transport equations to be solved. It would be wonderful just to go from 1,000 down to 10, for example, or to even to 100, which is still feasible on petascale and exascale machines. We know the manifolds exist because of the inherent correlations of species. They're not all 1,000 of them independent of each other. And there has been a source, the fact that there are correlations has served as a source of traditional paradigms for combustion modeling. So for example, using the mixture fraction or progress variable approach in flamelets. There's been a push in the last 10 years to start to look at empirically derived low dimensional manifolds, ELDMs, that are constructed from data. These are samples of compositions acquired from experiments or DNS. And these manifolds can be obtained from linear principal component analysis or from a variety of other nonlinear regression methods, for example, ISOMAP or MARS or other types of methods. Next slide, please. So what I'd like to do is to to develop a framework that would allow us to perform in situ reduced order surrogate models for DNS at the exascale for combustion. And so I've drawn here in this schematic what I envision to be the key elements of this framework, this computational framework. And we anticipate that this will run at scale on Summit and on future exascale machines. So that's the design of it. It will still keep the DNS data generator, S3D for the purposes of this prototype, but eventually Paley in other CFD codes. And that data generator would create the raw data in addition to identifying the quantities of interest, features, be able to detect anomalous behavior, and be able to provide reduced or coarse-grained data through filtering and averaging processes. But in addition to the traditional solver, DNS solver, we also want to include in situ machine learning algorithms. And in this initial cut at this, I'd like to include both static as well as time-dependent bases for reduced order models that can be applied to highly transient systems. And where the source terms in the reduced the species continuity equations for the reduced order models would be acquired from tabulation in the way of an artificial neural network. And in this case, we're probably looking at convolutional neural networks. And so we would want to have that tightly coupled with the solver and be very efficient on parallel machines, distributed machines. And so we also will have ability to do hyperparameter auto tuning and things like that. So that's what I would like to include in situ. And of course, as the run is going on, we're generating terabytes, petabytes of data that will serve the purpose of not only our own learning and our own problems, but also the data itself can be archived and be used for scientific machine learning and training and validation by others in the machine learning community. And so we're going to be very careful to provide metadata, provenance, annotations, and visual thumbprints and statistical summaries that identify all of the key spatial and temporal patterns as the run is going on, and save that with the data. Next slide. So to make this framework, I can't do this by myself. I'm going to adopt the co-design principles from an applications perspective. And so this is my team that we've assembled. And it involves computer scientists, applied math folks, as well as computational combustion scientists like myself. And it's a collaboration between the DOE labs and many in the universities. And so Tara Kachecki from NC State will be working on surrogate DNS with principal component transport. Hassam Babeh and his PhD student Michael Danello from University of Pittsburgh will be working on real-time reduced order modeling of sensitivities and data compression methods for very highly transient deterministic and stochastic PDEs. Their background is such that they'll be developing a lot of the foundational theory and algorithms. And then we'll be working with my postdocs at Sandia, Yukiko Shimizu and Martin Reith, who are going to implement some of these reduced order models for sensitivity, compression, and prediction of coarse grain models into the S3D code. Now, the framework for the S3D code and the in situ modeling, the software infrastructure will be developed, will be based on a task-based system called Legion, developed at Stanford by Alex Aiken and his students. And the Legion S3D code, which was developed out of the ECI project years ago, has now been rewritten in a compiled language Regent that is much less verbose and easier to read by domain scientists that sits on top of the Legion runtime. And then we'll also couple this with FluxFlow, which is a deep learning system that's intended to have very high parallel distributed performance in a tightly coupled manner with the solver. And so the team is looking forward to working with these folks, and many of them I've worked with in past projects, so we should be able to hit the ground running. Next slide, please. So let me just say a few words about the elements of this project. The first element is to look at reduced order modeling. And so I mentioned principal component transport. This is work that Tara Kachecki at NC State has been working on for the last 10 years or so. And so the idea is to reduce the high dimensional composition space needed to describe multi-component gasoline and diesel surrogates that would enable us to do DNS of these turbulence chemistry interactions for the PACE engine consortium. We will replicate the high dimensional composition space with low dimensions using PC transport, which is analogous to species transport equations, but coupled with deep neural networks to model the chemical and transport terms for the PCs. These are the chemical diffusion coefficients and the reaction rate terms for the principal components. And these will be done in terms of the transported PCs on the tensor processing units on Summit. And then we will also be able to recover the original thermochemical scalars from the retained PCs. The idea here is that only a few PCs we're hoping will be necessary to describe the all of the variance in the data, or 99% of it. And because the PCA analysis is linear, combination of species compositions, we can derive an instantaneous transport equation for the PCs, and that's shown here below in the red. And the chemical and transport terms in the PC transport equations are very similar to the species continuity conservation equations, except that the diffusion and reaction terms have to be modeled using deep neural networks that can relate them back to the transported PCs. And so we're very excited to try this out. And there has been some work done already that has demonstrated that there is a potential for over 2 orders of magnitude savings in DNS cost because of the much smaller number of PCs that has to be transported. And also the storage of data is reduced vastly. Next slide. So here's just an example, show proof of the pudding. Tarek and his students did an a priori DNS of ethanol compression ignition. They determined the principal components from slices of DNS data that I had from HCCI ethanol compression ignition. They retained a subset of the PCs, and then they reconstructed the solution for a bunch of intermediate species at different snapshots using the retained PCs. And what they found was, comparing the left column here, we see O2, hydrogen, and hydroperoxy radical from the full DNS data. And the right column then is the same set of species, but obtained from the reduced order model, the PCA and ANN tabulation method. And you can visually see virtually no difference between the 2 columns. The original manifold had 29 dimensions, 28 species plus temperature, and the PNN, ANN tabulation was able to only transport 2 principal components. And so there's a huge order of magnitude savings in computational time. And also there's a potential for reducing stiffness if some of the fast reactions are eliminated during this reduction process. Next slide. A posteriori, they found a similar result. So they actually simulated a reduced order model DNS, surrogate DNS, and with 4 principal components representing over 30 species and 184 reactions. The first 4 principal components are shown in the upper left right plot for this methane air premixed flame and wrinkled flame. And on the bottom, the isosurface plots show the CO mass fraction. CO, carbon monoxide is an important intermediate species. On the left is the full DNS, and on the right, a posteriori is the reduced order model, which has very low error and is virtually the same as the full DNS. So again, same story. You get huge savings, high accuracy, with much reduction in cost and storage. Next slide. So the next steps with PC transport, so far we've been training it on with static PCA from existing observational data. The next step is to try to see if we can evolve the PCs dynamically during the course of a full simulation. And this has to be done, reduction and modeling of the transport terms has to be done on the fly during the DNS. So this becomes a complex workflow. And we'd have to develop metrics to determine when the principal components are dynamically updated. And so we've been kicking around some thoughts on how to do this. And one idea is to augment with additional bases, not only the second moment that gets the variance, but also higher moments that might capture some rare events and anomalies. And so there has been some work looking at the 4th order kurtosis moment. And so outliers in the data, for example, here, if you have autoignition, which happens as a rare event initially, the second moment, which gets the variance, the principal vector lines up, just first principal vector lines up fine with the data. But if you have an outlier, say these pink spots that are igniting, the second moment the vector doesn't line up with that. It requires higher order moments to capture the outliers. And so we're thinking somehow to combine anomaly detection with PC transport to update the base dynamically the PC bases, and also to capture rare events. Next slide. Just a word on the anomaly detection method. This work was sponsored by ASCAC and led by my past postdoc, Aditya Kondori and Julia Ling and Warren Davis. And so, as I mentioned, they have developed an anomaly detection method that uses factorization of higher order moment tensors to be able to identify spatial and temporal regions where anomalies occur. And so we'll make use of this, and we've already started to implement this lightweight anomaly detection method as tasks on accelerators that we can include in our workflow. Next slide. Another method that we want to use in this framework and evaluate is one that Hassam Babeh at the University of Pittsburgh has developed called real-time reduced order modeling via a time-dependent basis. And it has two modalities, both observationally driven, data-driven, as well as model-driven. And the basic idea here is to develop a method that will generate adaptively a time-dependent basis that will capture the strongly transient phenomenon along a given trajectory in the system. The approach relies on either data from experiments or from DNS, as well as linearized equations of the system. The main idea behind the approach that Hassam developed is a variational minimization principle that will try to minimize the distance between the local vector field of the system that being constrained in the direction of the time-dependent modes and the rate of change of the time-dependent modes. And so the direct minimization of the defined functional here would result in evolution equations for the optimally time-dependent basis elements. And for the systems that are characterized by this unsteady response, these modes would then adapt according to the independently computed system history in a continuous way with the simulation, capturing at each time the transiently most unstable directions of the system. And so we plan to work with Hassam and his students in applying this method on the fly for both data and model compression, as well as for forward sensitivity analysis. So we'd like to understand, for example, the sensitivity of heat release or emissions to a large number of reaction rate parameters. And we don't want to have the headache of having to manage enormous amounts of data, for example, in using an adjoint sensitivity method, which requires backwards integration across the forward linearized state. And so this might be a real opportunity. Furthermore, this method is, provides knowledge discovery. The time-dependent basis discovers a low dimensional subspace of the systems that have these finite time instabilities and rare events, for example, ignition or extinction or flashback accompanied by turbulence intermittency. And so even understanding these dynamical systems, it would be a very valuable tool. And lastly, I would say is because it's not solving a large optimization eigenvalue problem, it scales linearly. The method scales linearly with respect to the size of the data and the low rank of the system. Next slide. And so this is just a preliminary example. Please play the video and that Hassam provided. And what it is a one-dimensional constant volume auto ignition of a primary reference fuel blend of diesel and gasoline with 116 species. So we've started it with the Gaussian hotspot and let it ignite. And what we're seeing is the temporal development of this hotspot during the buildup of a bunch of low temperature and high temperature radicals and eventual auto ignition at a time of about 0.6 milliseconds. And you can see from this, can you play the movie one more time? You can see this transient reduced order model captures the important hidden species significance, which increases a lot during the auto ignition process and then decays after the ignition process. On the left plot, upper right plot, is the eigenvalues of the covariance matrix, and on the bottom are the four evolution of the four dynamic bases. And so I think this method has a lot of promise in terms of reducing the subspace that one needs to transport and take care of for both data compression as well as reduced modeling purposes. Next slide. So to put this all together, we are using the testbed S3D programmed in Legion, this task-based, dynamic task-based system. It's a data-centric programming style and was developed with in mind to work well on heterogeneous distributed machines with accelerators and all kinds of other resources on them, compute resources on them. The method automates a lot of the aspects of getting high performance, such as getting not only data level parallelism, but also task parallelism. It automates details of how we schedule tasks and move data around on the machine. And does this by separating the instantiation of the tasks and the data in a separate mapping utility on the machine that knows about the domain science policies for scheduling as well as the underlying hardware. And so with that mapper, you can tune it and get performance portability across a number of architectures. So during the ECI days, Alex Aiken and his students created refactored S3D with this Legion programming model runtime, and in about 200,000 lines of Fortran, they converted that to C++. And in a weak scaling plot, you can see the comparison of the Legion C++ code versus the MPI-based code. So the throughput versus the number of nodes, I guess this is a couple years old because this was Titan, not Summit, shows about a 3x throughput improvement at low node counts and as much as a 7x improvement under large node counts because of largely due to the ability of Legion to hide the latencies going across the interconnect. Next slide. So we have also been very successful at using Legion to incorporate in situ analytics. For example, this is chemical explosive mode analytics. It's an eigenvalue solve based on evaluating the reaction rate Jacobian to identify different modes of combustion. The mode that we use SEMA in situ is we run it every 10 time steps or so as a diagnostic to determine what kind of flame you have, whether it's an ignition front, flame front, or an extinction front. The problem with SEMA is that it takes longer than a single explicit Runge-Kutta stage, and there's 6 stages per time step. And so if we had to manually divide the algorithm across the RK stages and interleave it with other computations, so as not to impact the critical path, that would have been really hard to schedule manually. But using the asynchronous task execution, we were able to schedule SEMA on unused CPU resources and took just about a day to implement. Next slide. And so if you compare the SEMA performance with straight MPI code versus Legion on 2 machines, this is the time per time step. We ran the performance tests on PISDAINT at ETH and on Titan. And you can see the Legion implementation. Can you push, not next slide, but yeah, there you go. We see that the Titan implementation results in an 84% reduction in the cost of the in situ analytics, SEMA, and we get it virtually for free, 98% reduction on PISDAINT using the Legion runtime scheduler. Next slide. So in the last year or two, we've refactored the code yet again using a Regent compiled code that sits on top of Legion runtime. And this Regent compiler allows application scientists like myself to be able to read and write code with sequential semantics. The previous Legion C++ code was fine, worked well, but you really had to be a computer scientist to understand it because of a lot of the verbosity of the code. And so we've rewritten it in Regent, and there have been a number of other codes, XFL, and some of the PSAP 2 and 3 NNSA codes have been written in Regent. It ports to exascale. We're porting, they're porting, I should say, Alex and Elliot are porting Regent to all of the exascale machines and all of the different types of GPUs. And one of the nice things with Regent is that it automatically compiles for different GPUs. Can you add the next click? It automatically compiles for different GPUs by just adding one command. For example, here we wanted to compile for a CUDA code. And so we don't have to emit a bunch of different types of code, slow codes, fast codes for different ISAs for different GPUs. The key features are similar to Legion. It just has transparent support for codes on CPUs and GPUs. It has expressive data partitioning for the distributed computation. Compiler and runtime manage the scheduling, the communication, the synchronization, data placement, copying. We don't have to do that as application scientists, and it's highly portable. Next slide. The last bit of the infrastructure here is the deep learning framework called FlexFlow. And this is also built on top of Legion, and it distinguishes itself from the commercial deep learning frameworks like TensorFlow and PyTorch in that it has an automatic search method based on a Markov Monte Carlo search algorithm to find high performance data partitioning in these networks. And it dramatically improves the locality and scalability and reduces the large scale training that we anticipate we're going to need on machines like Summit and Frontier from days to hours. In its current instantiation, it has a Keras interface to be able to interoperate with TensorFlow, and development is underway to also provide PyTorch support. Next. So to summarize, I'd like to say that this fellowship is an excellent opportunity for me to promote scientific and academic excellence in OSCAR and BES research through collaborations between the labs and universities. We're going to practice co-design, which has been very successful in the past. I think it's the right method for some of this work. We hope to be able to help train graduate students and postdocs through extended visits at the labs and generate a pipeline for future computational and data scientists at the labs. We'll develop an open source in situ DNS ML framework that can be used to evaluate other ML AI algorithms on these heterogeneous machines, and provide this framework will also be portable and allow different users to compose complex workflows with PDE solvers coupled with analytics, visualization, and machine learning. Aside from the framework, we will have data. It'll generate high fidelity data that can be used for training and validation of ML AI models, and we're going to carefully annotate the data. And in all of this, we're going to engage closely with the LCFs on issues of infrastructure and computing related to the large-scale simulation of these turbulent reactive flows and data storage. So last slide. So I'll just end. I'm looking forward to the next 3 years working with this wonderful team. Thank you.
Thanks, Jackie. Terrific talk. Questions for Jackie?
It's Vint. Oh, it looks like Tom has something. Go ahead.
I just wanted to congratulate Jackie on the award and all the work that you've done over the 30 years or so that you've been in the program. I was part of the combustion program back when it started in the early 1980s, and it's amazing to me to look at the progress that has been made over that period of time. It really shows you what can be done when DOE makes long-term investments in a particular area. And then now the collaboration with OSCAR, between BES and OSCAR on these types of problems, I think it shows you what a whole of Office of Science activity can really accomplish
by pooling their expertise and resources. So congratulations, Jackie.
Thank you, Tom. I remember those early days. What was it? CSMI, right? That even preceded SIDAC, I believe. Yes. I guess time has gone by quickly.
So Vint, and I see Dave also has his hand up. Vint, go ahead.
Me? Okay. Let me get my picture going. Oh, Jackie, that was great. I have a question about the trade-offs between uncertainties in your knowledge of the what the chemistry is actually doing, because that's either being derived empirically or by observations of experiments or maybe theory in some cases. So there's uncertainties there, as well as the uncertainties when you're navigating model space. And how does the machine learning help you navigate all those uncertainties and in some sense budget them?
Well, I think that's a research topic. We do have a lot of uncertainties, for example, in the chemistry, as you point out. A lot of the rate coefficients, even missing reactions, are still very much a research project. One thing that aspect that I think we can address is sensitivity, right? So how sensitive is my prediction of emissions, let's say soot, dependent upon getting certain elementary reaction rate properties correct? And so I think propagating this forward sensitivity analysis using these time-dependent reduced order models will provide that kind of information that otherwise you can't have access to without doing an adjoint problem, which becomes untenable when you have to do the data management. So I think that will then tell us what the sensitivities are, and we can relay that to the chemists, so they don't have to go off and make shock tube measurements in 1,000 reactions, but only maybe a handful, because those are the critical ones. And we can traverse a much broader space in turbulent simulations than they can test in a 1D shock tube or 0D reactor. They may not even know that their reaction mechanisms don't work when you traverse the turbulent thermochemical space.
One strategy we had back in the 80s at Livermore, the one across the street from you, is because we couldn't do the adjoint method to reduce from the big model back then for sure. We were doing a simpler problem even. But we would rather start with a very low dimensional known to be bad model and build it up with sensitivity analysis. And because we were starting with small models, it was cheap to do the adjoint calculation. And the idea is to grow the model rather than reduce it and try and fill out model space that way. But I don't know if that could be applied in your situation. It's all of these things are a bit different.
Yeah, I mean, adjoints have a problem with just the volume of data, because you've got to integrate backwards in time, and has a problem with dealing with chaotic systems, which turbulent flows are, right? So you can't,
absolutely,
kind of quickly becomes unstable.
Well, thank you for a wonderful talk.
You're welcome.
All right, well, Jackie, I've just reminded as well how much work on algorithms contributes to advancement just as well as what we've seen over hardware advances, but just phenomenal progress over the intervening years. And just congratulations for great work, and looking forward to seeing what comes next.
Thank you, Dan.
All right, let's move on. Bruce is going to give us an update on the 40-year report. I think this is the final, absolutely final, not kidding final this time version. So Bruce, the floor is yours.
Thank you, Dan. Hickman's pulling up my slides. Yes, I thought the last version was final, and I think you all did too, but there's been one more twist that I need to share. So next slide. So when I briefed you all in April, we were working on 2 documents. The initial charge to the committee was for 1 that had bifurcated to 2. Both of those I described as being on glide paths towards completion. And so I'm happy to report that both those planes have landed. So the Oscar history document is complete. It's a significant work. There were over 100 contributors. The final document is about 115 pages. You can get a glimpse of it here. That's the cover on the left. You can see a picture of a young Jack Dongara there in the back when he was a bad boy, as opposed to a member of the senior guard. And that's a picture of Rusty Lusk in front of some Argonne early computers on the right. So this is the style and the format of that document. At the bottom of this page, you can see a web link. At that site now, you can download all three of the documents that I'm going to be talking about here. Next slide. These are the authors. So this is a significant effort. I think went well beyond what the charge envisioned, but that was because this group of authors was committed to really capturing the remarkable history of OSCAR and its predecessor organizations. So I appreciate all of these people who contributed in many, many different ways. Notice the number of retirements that happened during this project. I'll say more about that later. Next slide. The second document that we were working on last time was this companion document that was designed to be a little more accessible, a little more visual, targeting a different audience, a bit less technical. So it's more of a magazine as opposed to a book, might be the right metaphor. So it's 44 pages, 10 articles, 15 sidebars. You get a sense for its visual layout from the two little screenshots of pages here. I will take great pride in the wordplay on the turbulence title there. You can see the human element. These are not just technical documents. They're talking about the full dimension of OSCAR's impacts, including things like workforce and CSGF. So next slide. Here's another snip from what that document looks like. The way that we executed this was the committee, the names that I alluded to earlier, generated article ideas, basically thrusts of narratives, but it was technical writers under the leadership of Bill Cannon and his team at Krell that actually wrote the articles, and a subset of those committee members then shepherded and helped with the editing for correctness of all the individual articles. And it seemed to be a very effective process. And so the product, as you can see, is visually very compelling. And I think it's at a very nice level. So when we met in April, I didn't think we would need to meet again because this is where we were headed. And I'm pleased to say we're in great shape on these two. So again, both of those are at that website from the earlier slide. So, however, a few weeks after the last ASCAC meeting, Chris Fall and Harriet Kung, spurred on by John Sorrow, expressed interest in building upon the materials that we had gathered and produced to use in an educational campaign around OSCAR. And they asked for a different set of materials or some of this content repackaged in a different way. So specifically what we've done is we followed the model of, many of you have seen these BES one-pagers, these simpler sets of materials structured in a very consistent way and in a way to communicate impact for both advocacy and educational opportunities. And so that's what we did. We followed that model. I am drawn to this metaphor of the Pony Express riders who would ride a horse as far and as fast as they could until the horse collapsed exhausted, and they hopped on another fresh horse. And so the previous committee members, I think, were pretty done with this project. So I needed a new horse, and so I reached out to the OSCAR points of contacts at the major laboratories, and they stepped in with enthusiasm as content developers and shepherds in the end, what we settled on was 11 one-page briefs. They all have a common structure and layout: intro, innovation, impact, and takeaway. And again, Bill Cannon and his technical writers played a pivotal role in revising the content and then producing and packaging everything to be visually compelling. So next slide. These are the 11 topics and the authors of these little one-page documents. You'll see a few names that are descended from the previous author list from the longer documents, but also many new names. And those new names are the points of contact, the ASCAC points of contact. Next slide. So this is what these one-pagers look like. This is the top half of one of them. So you know, an eye-catching visual at the top. On the left there, you can see an introductory paragraph, then the innovations, impact, and there's a takeaway that'd be down at the bottom, just a one-sentence description, maybe 2 sentences of the key message. So next. Here's another one on uncertainty quantification. Again, exactly the same structure, but with a different image. Next slide. And yet another one. Here, this one on facilities. And again, you know, compelling, eye-catching images. But you can see this recurring structure, so it's easy to use these to entice someone in. Can you go back, please? To use these to entice someone into our world and into the educational materials, and perhaps what their appetite to dip deeper into the prior 2 documents. All right, next slide now. So I want to thank everyone who contributed to these efforts, all the names I mentioned before. Paul started out the project and handed it off to me when he retired. As I mentioned before, this project seems to have been driven a number of good people into retirement. So I hope that's coincidence and not causal. Tiffany played an enormous role, particularly in the lengthy document, the historical document, in keeping us on track, and tireless editing and correcting and multiple times and multiple phases. I've already mentioned Bill Cannon and his team that produced these lovely later 2 products, the magazine and then the one-pagers. And then there were a small number of people who actually had the endurance to stick with all three documents. So I've listed them here. I want to mention John Basher. He actually delayed his retirement at Berkeley because he was enjoying this project so much, and then continued to work on it after his retirement. And so it was deeply appreciated. John Sorrow played a substantial role in thinking strategically about the structure of this whole activity based upon having done something similar for BES, and that was extremely valuable. Phil retired midstream, but continued contributing in retirement. And then let me just call out Buddy, since he'll be speaking next. As usual, as has been true throughout his career, he was the epitome of professionalism and grace in the execution of this project. So that's all I have. I'm happy to take any questions you might have.
Any questions for Bruce? Well, let me just say, echo what Bruce said. Thanks to Bruce himself, but also thanks to everyone who worked through what we thought was a pretty straightforward, simple, short process at the beginning. It has turned into a marathon along the way. So let's please not, for Bruce and the committee's sake, let's not suggest a 4th idea. If we do, we'll charter a new committee.
My network connection's breaking up. I can't hear you, Dan. I'm leaving in.
Well, I was just saying thank you. And
no, I was kidding. I don't want you to even think about a 4th.
Any questions for Bruce or anyone about the 4th document? All right. Well, we really do appreciate it, Bruce. So thanks to everyone who's been working on this. I know it's been a long and a mighty effort, but really worth it. Next up is Bruce alluded to Buddy. Buddy's going to offer a few reflections on high performance computing.
Yeah, but I think we had someone who wanted to introduce him. Bob.
All right.
Yeah.
And you did. Can you hear me?
Yes.
Yeah, Bob, go ahead.
Howdy. Well, good afternoon, Dr. Reed and committee. I know it's been a long time. and especially glad to be able to introduce Buddy. He and I go back a bit. You know, when he started out, who knew that this guy from Hattiesburg, Mississippi would end up serving his country as a lieutenant in the Air Force and introduce supercomputing to the U.S. Air Force as they stood up the first Cray computer ever out at Kirtland Air Force Base, the weapons lab. That's where I first met Buddy. He was there before me, but I came in and I met him there. He was a systems programmer, and he was primarily responsible for standing up that system. But once he fulfilled his commitment, he was going to leave the military, something which I never quite understood at the time. But he wanted to go to and help them stand up their first Cray computer, an XMP there. So like I said, I never quite understood that. But 20 years later, I came back, and it all became clear to me. Buddy was there. He was helping Oak Ridge become a leader in supercomputing for the world. I mean, at the time he got there, I don't think it was the power you see today. And then during that time, he worked hard. He moved up through the structure there and finally became a program director for the OLCF. And in doing that, he provided 3 #1 computers for the nation, which was an important thing at the time. If everyone remembers that we were and still are battling Chinese and Japanese and everybody for world leadership in that area. So I think more importantly, though, not only did he provide the machines, but he delivered the tools that the nation needs for its most demanding problems. I like to think that when the nation calls, the machines that Buddy brought to full operating capability were those things that enabled scientists to provide the answers like no others in the world can do. So kudos, what a great career he had. But it didn't end there. I mean, who knew that when he left Southern Mississippi, he'd be responsible for leading a team that would install the first exascale computer for the nation. So I kind of think from megaflops to exaflops, but he's dedicated his life to serving his country. And I think that's important, and we want to recognize that. But with that kind of dedication, of course, comes wisdom. And as we close the session today, I think, or at least I want to commend Buddy to the committee to share some of that good stuff with the rest of us. Buddy.
Well, thanks, Bob. I had no idea you were going to introduce me. Let me see if I can share my screen here. Get this going. Where's the screen I want to share? Hold on. What are you guys seeing?
We're seeing you.
Okay, it's still seeing me. Okay, I'm still trying to figure this thing out. I am not somebody who has spent a lot of time on this. Give me just a
like the rest of us. Well, let's see. If you clicked on share screen, then the only question is which front.
Yeah, that's what I'm trying to figure out, and I'm struggling. Hold on a second. Why can't I find this?
Look at the bottom.
Yeah, well, it's nothing's showing up on the bottom.
Hey, buddy, this is Doug. Fielding big computers is a lot easier, isn't it?
Yeah,
I was going to say,
absolutely.
maybe you need an exascale system.
Actually, my wife was trying to teach me how to do this last night. So I don't really do this. Okay. Okay. Share the screen. Screen I want to share. Screen.
Pick whether it's a
Now we need to go to, you still seeing me or are you seeing the script?
Yes. No.
Well, I don't know what I'm doing wrong here.
What should be happening is you click on share screen, it's within that window that you would make the selection.
Do you have 2 monitors?
I have 3 monitors.
Oh,
That's your problem.
Oh,
Do
really?
you want Hikmet to share them, buddy?
Wait a minute. Did that work? No.
No.
Okay, Hikmet, I just sent you my latest version just a minute ago. If you can use that, that would be great.
There's
And
a
I
really bad
apologize
joke
for
in here about
not being able to do this.
There we go. Hey.
All right, Habermas PowerPoint.
All right, buddy, it's up.
Okay, good. Well, I want to thank each of you for this, and thanks for Christine and Barb for inviting me to do this. I have, as Bob said, I actually worked for him for about 2 weeks, I think, when he was coming into the weapons lab and I was leaving the weapons lab to go to Kirtland Air Force Base and teach ADA for a year before coming to Oak Ridge. And I've been at Oak Ridge now for 36 years. And I'm getting ready to retire here pretty soon. So I wanted to, Christine and Barb asked me if I would be willing to say a few words. So I want to thank them for that opportunity and all of you for such nice words. And again, thanks for hanging on late on a Friday afternoon. I know that's not what anybody wants to do. Okay, next slide, please. So the fine print here, you know, every presentation has some statement in it. Well, you know, these predictions that we make and we don't always have such good views into the future of exactly what's going to happen. And so they're often difficult. They're always difficult and often wrong. So I pulled out my, you know, my magic 8 ball and it says reply hazy, try again. So we'll see, we'll try again, but the statements here do not necessarily represent the Oak Ridge National Laboratory or the Department of Energy. Okay, next slide. So I've really enjoyed working on the ASCAC report with Bruce and the entire team that was there. It was a really a very good team, did a great job putting this together. But since that so closely matched my time that I've worked in HPC, I thought it would be appropriate to think about where we've been and where we're going. So this chart shows just some of the systems that I've worked on. And oh, I would be remiss if I took credit for all of the work that all of the people around me have done, as was said in the in Bob's remarks. I mean, I certainly had a part in some of these, in many of these machines, but I did not do nearly all of the work. We have a very good team, world-class team in high-performance computing, and they were responsible for far more than I ever did. This chart shows just some of the systems I've worked on. You can see the groupings, the color groupings. I mean, we've gone from mini computers like the VAX to vector machines, and then massively parallel, and now hybrid CPU and GPU systems such as Titan Frontier and Titan Summit, and next year Frontier. You know, each one of these architectural changes reflected the end of one type of technology and requiring a change to a different technology to increase the performance. So, you know, for example, the vector machines that used emitter coupler logic, well, when that kind of ECL technology ran out of gas, we kind of had to switch to CMOS. CMOS has been running very well for a long time as we've ridden that Moore's Law curve, but we're kind of reaching the end of that, and with the end of Dennard scaling, we're having to find out where do we go from here? But really, the hardware is only a piece of the performance story. Software improvements account for a really large part of the performance improvement of applications. We've had better software in the form of mathematical methods, improved solver precision, improved accuracy and performance, better development tools, and new versions of applications that take advantage of the latest architecture. These have accounted for a large part of the improvement of the performance that we've seen. And much of ASCA's investment in these areas have come through the SIDAC program, which I guess we're getting ready to go into SIDAC 5, as Barb discussed yesterday, as well as the Exascale Computing Project that's supporting approximately 50 applications and 70 software tools, including libraries, compilers, debuggers, profilers, etc. And yes, so I'm not going to try and go through all of these because, frankly, I'm not a mathematician. I don't know what some of these things do. But these are, this is a list that I pulled somewhat out of that 40-year anniversary document, some of the things we worked on. The complexity of systems, next slide, slide 5. The complexity of systems has also grown tremendously. The Cray 1 had approximately 200,000 gates and used 70 square feet of floor space. A single IBM Power 9 processor on Summit has 8 billion transistors, and each NVIDIA Volta GPU has 21 billion transistors. There's about, depends on the way they do the gates, but there's between 2 and 4 transistors per gate. So you can do the math yourself there, but and Summit uses about 8,000 square feet of floor space as opposed to the 70 of the Cray 1. So we've things have changed a lot over the years. The software complexity is just as daunting. Programming a hybrid CPU GPU system is more difficult than using traditional HPC CPU only machines. The Cray 1 had a single CPU with several functional units that provided just real small levels of parallelism. Some of today's largest systems have tens to hundreds of thousands of nodes and billions of threads of execution. Managing multiple levels of parallelism and different instruction sets between CPUs and GPUs is in a system takes a lot of skill and experience along with the right tools. And on top of that, we're having fewer and fewer vendors because things are getting gobbled up. I mean, you can see, for example, the PGI software, PGI compiler set, which we use on virtually all of our computers until just recently, PGI was bought by NVIDIA. Alinea provided debuggers and performance tools, and that was bought by ARM, and that was bought by NVIDIA. And now Mellanox has been bought by NVIDIA. So, NVIDIA is obviously aspires to and is becoming a world leader in high performance computing. But there are fewer and fewer opportunities for others to use some of that same technology, such as the compilers and debuggers and so forth that we've used for years on lots of different machines that have come from many different vendors. We also, facilities are just amazing. When I was in graduate school in computer science, I never even thought about the space and power and cooling needed for computers. Turns out I also needed to have degrees in mechanical and electrical engineering to go along with that. At ORNL, we have an order of magnitude more space available for computing. When I started, we had about 7,000 square feet above the library on a raised floor, not a raised floor, but on a floor that could hold 60 pounds per square foot. We actually did get a Cray X1 on that raised floor, but we had to put in a lot of bracing to support that. now we have 70,000 square feet, and the raised floors we put in where we have them can hold 600 pounds per square foot. And in some places we're just, as Summit sits on bare concrete, so it can hold even more. We've also increased the power and cooling capacity from 2 megawatts when we first moved into our computing building to right at 100 megawatts, just less than 100 megawatts. That is, by the time we finish installing all the power that's in cooling that will be required for the front. So, you know, things change a lot in a few years, don't they? I mean, you look at the, going to slide 6, you look at some of the work that we're doing on the facilities. Primarily, this is cooling part of the facilities for the Frontier system. In the upper left, you can see some of these cooling pipes. I mean, those cooling pipes are about 36 to 40 inches in diameter. So really large pipes just to bring the cooling water in. And this big red crane in the middle lifts those up and puts them on the top of the building. Over on the right, you can see the platforms. I didn't have a picture of the cooling towers actually on top of the building since we've been working from home so much. I haven't been out there to take pictures very much to see exactly how it all looks today. You can see in the middle of the bottom row pictures, that's the main computer room where Jaguar sat and where Titan sat. We decommissioned Titan about a year ago, a little more than a year ago, and have been working on preparing that space for the for Frontier, and so that's moving along well. And then you know, along the way you find out that sometimes you just have to do something that's a little weird and build your own tools. So in that computer room at the bottom, before we took the raised floor out, we had a few systems that we were keeping that we needed to move to upstairs into a different location. So our facilities team was looking at how we were going to move these things, because if you've got a cabinet with 600 disk drives in it and you pull all the disk drives out and then move it, you're never going to get them all back in there in the same order, even if you try really hard. And even if you do, you're probably going to break some pins and something's not going to work properly. So our facilities team actually came up with a dolly that we could bolt onto the side of a disk cabinet, lift it up, and then roll it down the hall and not have to jar it so much and create problems in it. And that worked remarkably well. So, you know, it's not only the computing people that make these systems work. The facilities people are a huge part of what we do. Going to slide 7, wanted to say something about the requirements, the leadership computing requirements. What are we, what is it required, are really outpacing what we're doing in the commercial marketplace. So, we need more cycles than we can buy from the commercial marketplace today. So the number of leadership systems is very small. If we define, there is no hard definition for what a leadership computer is, but if we define it as the top 5% of the performance on the top 500 list, then on the June 2000 list, there were only 10 leadership systems in the world. So what's the implication of that? If you only got 10 of them, there's not very many vendors are going to be coming to this business. So we have a relatively small number of vendors that are actually trying to sell or trying to design, build, and sell these leadership systems. And it requires R&D funding through government channels to make that happen. Traditional HPC applications require very high memory bandwidth and interconnect bandwidth, in addition to high performance in the floating point operations per second. But not all of the commercial applications require that very high bandwidth. And so, if bandwidth is the most expensive thing you can deliver, and I would propose that it is, most systems sold don't require, and if most systems sold don't require it, then the vendors aren't going to build systems with very high bandwidth. without somebody paying for the engineering work, the NRE work, to pay for that R&D. And those systems will be very expensive. So it is possible to build commercial cloud systems that can meet these leadership requirements, but the cost of the bandwidth is prohibitive unless you're using those, you're selling those cycles to somebody all the time and you keep it very highly utilized. You know, we run our systems at somewhere, you know, between 90 and 100% utilization most of the time. The leadership, for leadership systems, the cost of using the commercial cloud is at least 2 to 3 times more than having the computers in-house in work that we've looked at and that we've priced out. And there are instances of cloud computers that are cloud systems that have supercomputing architectures, but none that are really leadership class in the definition that I proposed in the first bullet on this page of the top 5%. It's just too expensive if you don't run those systems at 100% utilization, and the cloud's vendors typically don't, from what we've seen. Okay, going to slide 8. What's next? What are we going to do next? Well, now we bring in the magic 8 ball telling us that it's a little hazy here. So the transition to accelerator-based nodes using CPUs and GPUs has given us a big increase in performance and efficiency. You know, speakers today have talked about how you need that increase in efficiency. So what do we do to get similar gains? Well, quantum computing certainly has promise, but it's got a lot of complexity too, and I think we're still a ways from having large quantum systems that can solve you know, a wide range of applications. You know, the quantum work that was talked about yesterday and the facilities that are standing up, we hope that will bring that to us over time. Artificial intelligence, I mean, you hear about that everywhere you go today, and it may get us the answers to some of the problems that we have without having to compute the answer, but it certainly isn't appropriate for all the types of problems that we do. And the cost of current leadership systems is approaching $1 billion per system. And if it has a nominal 5-year lifetime, you know, that's a lot of money. So this is a very capital intensive business. So I believe we need an all of the above strategy to successfully build next gen systems. We need R&D into new devices that are more efficient. We must leverage commercial technology. There's just not enough money for us to do custom technology for these systems. We have to have use off-the-shelf technology where everywhere possible. The calculations need to be done in the most efficient way possible. We got to be very aggressive at turning off circuits that aren't active. So, you know, for example, the NVIDIA systems, when we started running Titan, that system would typically run somewhere in the neighborhood of 5 megawatts when we were running just our normal workload on the machine. We went up to Summit, which was several, you know, went from, what was the number? Went from about 1 petaflop, I can't remember the numbers now, but whatever. It was much faster, but the power didn't go up very much, because if you weren't using every one of those functional units in the GPUs, it would shut them down very aggressively. So we didn't waste power. And we must continue to improve algorithms to be more efficient. I mean, the reduced precision that these GPUs have in some cases can give you tremendous benefits in the performance of the machine, as we saw in some of the early work on those machines on Summit when it first came out and won the Gordon Bell Prizes. Let's see. The next slide, slide 9. So what might a computer that does this look like? Well, it may not just be a computer. Instead of a leadership computer, it may be like an exascale ecosystem. So a lot more heterogeneity to improve the efficiency, but as I said, use off-the-shelf technology wherever possible to reduce cost. Distributed powerful computers and storage, distribute the computers and the storage so we don't have to move all the data back to some central exascale system every time we want to use it. Each of the components in the environment needs to be tailored to the task that would be done at that location, and then only move the data and the calculations to the big exascale computer if it's needed to solve a problem. So next slide, what that might look like, you know, physically at Oak Ridge, what we're discussing is, you know, we have our supercomputing facility, the OLCF, and we'll have our exascale system next year. We have other user facilities that need high performance computing, and but perhaps not everyone needs exascale all the time. And so, you know, at our manufacturing demonstration facility, our biological sciences, spallation neutron source at the Nanophase Materials Center, they all need very high performance computing, but we would like to be able to put computers at each of those facilities that could be edge computing to help do those calculations more efficiently closer to where they're needed. And then only move the data or the calculations to the biggest supercomputer when we need to do that to solve a problem that can't be solved at the individual edge sites. So slide 11, Jim Hack gave me this slide and I thought it fit in well. You know, predictions in technology space are dangerous. Clifford Stoll said about the internet in '95, the truth is no online database will replace your daily newspaper. No CD-ROM can take the place of a competent teacher. No computer network will change the way government works. How about electronic publishing? Try reading a book on a disk. Yet Nicholas Negroponte, director of MIT Media Lab, predicts that we will soon buy books and newspapers straight over the internet. Yeah, sure. Well, within 15 years, you know, many print publications were exclusively online. And then Dave Pogue, talking about the iPhone, or talking about Apple and moving forward, answer the question, everybody's always asking me when Apple will come out with a cell phone. My answer is probably never. It just ain't gonna happen. Well, in less than 9 months, the first iPhone was released. So, you know, so what I've said, take it with a grain of salt. All I know is what's next for me. I'm gonna go have a good time with my grandkids. I am working over here, Barb, on making sure that we have, you know, the next group of people coming in to take on the systems and for workforce development. So, you know, here's my granddaughter with her father, sorry, telling her how to, helping her figure out how to run his computer. And so I'm looking forward to spending more time with them. And I just want to say, I really can't think of a better place or a better group of people to have spent the last 40 years with than where I've been working. And I'll miss all of you. Hope I get to see more of you over the years. With that, can I answer any questions?
Well, buddy, thanks for all the amazing things you've done. There aren't many people who see that many orders of magnitude transition in a technology during their professional career. So thanks for everything that you've done for DOE and for the country. It's really appreciated. So any questions or comments or kudos for Buddy that people want to offer before we go?
Yeah,
yes.
You just need to let us know if there's life after retirement.
Well, you know, some people fail retirement. I'm hoping that that I don't. Actually.
Dan, I had a question, if I may ask Buddy,
Sure.
and pick his brain. Buddy, on the bandwidth slide, you talked about the supercomputing bandwidth needs to be an order of magnitude more than commercial clouds or data centers. But from my naive view, the commercial crowds are driving actually the bandwidth standards in data centers, and the east-west bandwidth, or the bandwidth between computers, is actually, since they have a distributed way of solving problems, is with MapReduce, it's really high, and they are driving the 800 gigi standards and others. And that's what's being talked about, at least in the commercial sector, as what's driving bandwidth, and not supercomputing centers and their requirement for bandwidth. So I was very surprised with that.
Yeah, so either I wrote it wrong, or maybe I said it wrong. What I was talking about when I was talking about the bandwidth needs of the applications, I was talking about memory bandwidth, to and from the CPU in the memory, as well as the interconnect bandwidth in these parallel systems, not necessarily the wide area bandwidth connectivity that ESNet needs.
No. I was talking of data center bandwidth within the data center. I was talking of network bandwidth interconnecting nodes within the data center.
Okay.
And I'm not talking of ESNet bandwidth, because obviously the bandwidth needs of the interconnect are much bigger than the wide area needs. But from what I get to understand, I'm watching some of the EEE work that is going on, is data center is the driver for 800 gigabit Ethernet and other things.
Okay.
So I was just wondering okay, I was just trying to compare and contrast, that's all.
Yes, go ahead.
It's Vint. I would like to confirm Inder's observation. The data centers are just unbelievably huge consumers of capacity, just because of the number of things and the data rates that we have to move around inside the data center, let alone between them.
Sure.
All the time, because we're always copying everything all over everywhere.
Well, hopefully we won't have to do as much of that copying as we go forward with our edge computing.
One of my observations when I went to Microsoft, having thought I was a big iron guy, what I realized was I was a fast iron guy, that there was a scale there that I had never seen before.
No, I realized that we're not anywhere close to the size of the big commercial data centers, but it is, but we run a different programming model in that we have to have all of a group of processors working together on a single application, which often they don't have to have.
Well, even buddy, it's Vint. I hate to be a pain in the butt, but just mention, think about indexing the entire World Wide Web. We have to suck in an enormous amount of data, then we have to, sort through it, and we have to give you answers in 0.018 seconds. So for certain applications, there is a comparable kind of capacity requirement. But I will say, for certain kinds of computations, like the ones that many of which we've been talking about today, that we don't have to do that in most of the data centers. But you're going to see a shift in that direction, I think, as the commercial demands increase, and even as government requires the use of data centers from more conventional companies.
Well, okay, we will see.
Well, that's why we play this game, is to get answers to those questions.
Yeah, that's right.
Well, like I said, thanks for all that you've done over the years, buddy. I know I speak for all of us, and you can see that in the kudos in the chat.
Well, thank you. I very much appreciate it.
Yeah. Yep. Applause to you, buddy.
So we're again past our time limit, but lots of good discussion and presentation. So any sort of parting issues people want to raise, either the committee or among the other 100 people who are with us today? All right, well, hearing none, please take care of yourselves, be safe and healthy, and let's keep chasing the future. Thank you for all that everybody's doing.
Yes, Thank you all.
Bye.
Safe weekend.
Thank you.
All right.
Bye.
Take care. Bye-bye.
Bye, everyone.